happens after the course. We'll be provided a YouTube link for that. I'm currently in Norway, actually, visiting some family. So if you hear one of my nephews in the background here, that's just him playing a little bit, but should be hopefully not disturbing the course too much. The course today will be very practical, trying to be hands-on. We'll do a little bit of theory, then we'll actually everyone here go through a well together, a little bit more theory, and then we'll do a second well, and then we'll see how much time we have in the end to go through a few interesting topic that has been asked by the audience. I have a couple of colleagues here with me today. Elena is here, Mo is here, Curtis will maybe also join parts of the course here. So if you have any questions as we go through the course, feel free to ask them as we go. And if Mo, if you can just mute folks who are not unmuted, that would be great. If you have a question, feel free to unmute and just ask the question, or ask the question in the chat. Everyone should have software access to Whitson Plus. Just remember that in the course, we're going to use courses at Whitson.com. How do you access courses at Whitson.com? You just go to courses.whitson.com on the web, and then you log in there. And what you log in with, if you're, just show how it is when you log out, is you just put your email and username into this first one here, and the password is just what's on the screen right here, and what's communicated in the email. It's just Whitson with a capital W, RTA 2022. So that with that you should be able to log into, again, courses.whitson.com. Okay. So if you have any issues with that, just let me know. Okay, and then when you, hopefully this works. Let's see. Yeah, and when you're logged in, it should look something like this, and we'll spend a little bit more time in the software a little bit later. If you're not able to log in, just send an email to Mo, or just write in the chat window. And his email is just dahook@whitson.com, and a lot of you know him from before. Again, I'll just mention it the last time. Don't use your company domain. So all of you obviously have or access to the software through your company, but this is primarily one for the course, and you all should have been set up with a particular project for each of your names. So I see all of the projects since I'm the support user, but you all should just see the project main and your own project. So just let us know if you are not able to log in. Just as an introduction, this is the third of 3 courses that are so-called half-day courses on specific items related to RTA. We've already finished the PVT course, which is a part of the Numerical RTA JIP, and also for folks that are joining in the industry, that's possible to join there as well. We had one dedicated to bottom hole pressures, and both of these aspects are very important inputs to RTA. And this is the first course that we have as a part of the JIP directly related to RTA. So today we'll cover both analytical and numerical RTA, and we're also going to do stuff in the software, which is going to be fun. Next month, there's a similar course, but it's dedicated to flow material balance only. We'll mention a few things about flow material balance today. That's the methodology that comes out of Cimarex with Leslie Thompson and Barry Ruddock and Narayan there. So that's going to be much more in depth on some of the theory, but also a bunch of different use cases and a lot of use of this recovery factor analysis feature as well that's coming in tandem there. There's also a final course that is a part of the last knowledge sharing session in the end of Q3. And if you want to join any of these courses and you haven't received an invite to the course yet, just send an email to myself. And also, if you need a course certificate for registering these hours for different training purposes, then just let me know, and we'll make that happen as well. What we'll cover in the course today is Whitson Plus and RTA basics. So that's everything from just logging in and accessing the tool, the workflows themselves, and of course general structure and functionality. There's a lot of things coming into Whitson Plus all the time, and the tool, the toolkit is primarily focused around RTA and well performance. So it's always good, even for those that are more seasoned, to go through this a little bit systematically, sometimes as well. But we'll not do that in an isolated manner. We'll also go through a lot of the RTA and focus on RTA primarily. So that's classical RTA, which is typically what we think about as the square root time plot. Numerical RTA, which is what we think about as the so-called Bowie workflow. And we'll also have a little bit of things related to the so-called fractional RTA concept out of Chevron. So the thing that we'll assume, though, is that most of the inputs to the analysis are correct. So the inputs to RTA is PVT, it is bottom hole pressures, and it is production data. So we'll assume that all of those inputs are correct in at least the examples that we're working on now. You can change a few of the things if you want to, but uncertainty related to PVT and bottom hole pressures and what impacts that, etc., was addressed in previous courses. So we'll kind of be back to basics in this course. What we'll not cover is details related to these other topics that have dedicated courses related to them. So PVT, bottom hole pressures, and multi-phase FMB. We'll also not talk about data integrations, which is of course interesting for many of you all, and we're working with many of you all on this already. So getting data into the product on an automatic basis to, for instance, perform bottom hole pressure calculations, etc., etc. So some of these advanced topics we're leaving out for today. We'll also try to keep the course very practical. I'll not go through any derivations or any very advanced equations, or if we show an advanced equation, I'll try to convince you that it's actually not very advanced stuff that we're dealing with. I also believe in repetition. So that's why we're going to go through kind of everything from A to C in a nutshell really quick, probably here in the first hour. Then we're going to run through a case together. And then we're going to go through everything a little bit more in detail and go through another case together. And if time is on our side, we'll probably be able to do even the third case. So we'll see a little bit how well we're doing on that. Before we go there, the question that we get a lot is like, okay, RTA sounds great, but what do you actually use RTA for? So RTA is when it comes to use cases, it's a technique where you use both rates and flowing pressures to quantify essentially productivity and your contacted pore volume. So that's the productivity is A root K, typically correlated to that. And the contacted pore volume is how much of the reservoir you'll be able to contact with your well after you've stimulated the rock. So once you've quantified an LFP and an OIP or an OJIP, then you can use that to compare well performance with each other on a consistent apple-to-apple basis, especially if there's big differences in drawdowns, for instance, or fluid types, etc. A lot of us use it to get more comfortable with our physical forecasts or sanity check physical forecast or constrain them, especially in multi-phase systems. Some of us also use it for to assess completion effectiveness and frac optimization, to look at production optimization and drawdown management, and also a lot of us use it as a starting point for more advanced studies. And it all goes back to this concept of it's better to be roughly right than precisely wrong. Most of these techniques you're able to do in less than 10 minutes per well if you start to get seasoned on it, and even if you just have done it a few times, you'll be able to get actionable outcomes fairly quickly, is at least our experience. So the other thing that we'll just remind ourselves on here is kind of what we see as the unconventional reservoir workflow, where we get PVT data, typically from equation to state models. We'll revisit that in a sec, to run bottom hole pressure calculations. And once you have PVT, bottom hole pressure, and rates, you can do a flow material balance exercise We'll discuss this slightly in the course today, but not too much. And then you can use that to constrain some of your analytical and numerical RTA workflows that you can then finally bring into a numerical modeling exercise. And our focus today will be related to these two parts right here, part 4 and 5. So a little bit more in detail on those two things. To really understand RTA, as I always tell at least people who have never been exposed that much to RTA before, what is really important when it comes to RTA is two things primarily. The first thing is flow regimes, and the second thing is what you can actually derive from RTA. So if you know these two next slides, you basically know RTA, or at least you're dangerous at that point. So there's 3 flow regimes that we'll talk about in this context, and that I think almost is, at least that are relevant for tight unconventionals. It's the so-called infinite acting flow regime that ends as the pressure transient reaches one reservoir boundary. And then you have a boundary dominated flow, which is the opposite extreme, that starts as pressure propagation, reaches all of the reservoir boundaries. And then in between there, we're talking about what we call transitional flow. So you might have seen one of the reservoir boundaries, maybe the interfracture boundaries, but not all of the boundaries in your system, maybe the well-to-well boundaries. So what we'll see here, and hopefully convince ourselves, is that all of these flow regimes can be more or less important, a wide range of different places in unconventionals. And we'll talk about this a little bit more later in the course. The second thing is like, okay, it's very important to understand the flow regimes, but it's also important to understand what we can uniquely derive from RTA. And the one thing that I mentioned already is the productivity term, like the LFP term, the A root K, that you will use that interchangeably throughout this course. So linear flow parameter, LFP, and A root K, same thing. The second thing is the contacted oil or gas in place. That's how much of the reservoir after call it a completion job we're able to contact. But it's also important to remember in what circumstances can we actually quantify these, because in theory we can derive both of these from RTA, but we also need to know which flow regimes we can derive them from. So LFP we can actually only observe like the correct value during infinite acting linear flow. And the oil in place can only be observed during boundary dominated flow, which means that if you have a system that goes straight into transitional flow, straight into boundary dominated flow, your LFP is kind of tricky to quantify. And the same goes the other way around. If you're still in infinite acting or transitional flow, even, you can't with certainty say what your oil in place or gas in place is. And if you don't know your oil and gas in place that a well is contacting, then at least by definition, it's impossible for you to know what your EOR is. So these things are really, really important. So the 2 slides that I showed you now, those are the 2 slides that I kind of hang up on my wall and always remind myself when we do analysis on these things. Volume that we resolve from RTA, that's we called it a lot of different things, but just to make that kind of visually or in an illustrative manner extremely clear, if you look at this box right here that we put 3 wells in, and then we say that everything inside of this gray box is the petrophysical mapped in place volume for this pad or whatever, and then we're able to complete the system after a period of time with of course some kind of completion scheme, and then we're able to contact what's actually here in blue. So not everything in the mapped in place volume, but a subset of that. And that subset, that blue volume, is what we call a lot of different things, okay? And that we asked the audience here in, I think, the first knowledge sharing session what people call it. And some people call it the contacted pore volume or the contacted oil or gas in place. Some people call it the stimulated rock volume, and others just use these interchangeably. So call it drained rock volume or mix and match. But what is important for me is that you're not mixing the volume that you're deriving from RTA with, for instance, mapped in place volumes, because that was the other exercise we did in the first knowledge sharing session. We asked all the participating companies if they've compared the oil in place and gas in place from RTA to the mapped in place volumes. And you know, there was a pretty big haircut there. And I think most of the answers for oil wells, for instance, was between 20 to 40% of the mapped in place volumes. So it is definitely a smaller subset of the resource we have in place. When it comes to quantifying this contacted pore volume that we saw, this blue area that we saw earlier, we can quantify that in many, many different ways. The most important thing for me is that no matter which of these terms that I use, the pore volume, the oil in place, the gas in place, and even the water in place, I'm talking about the same thing. The only difference between these are PVT properties, basically, or fluid properties with initial water saturation. So in the course, I'll probably use all of these interchangeably, so just remember that. And all of them are correlatable. Only difference is PVT, basically. So everything is kind of the same, but it's still a little bit different. Before jumping into a lot of the material, you know, when it comes to flow regimes, it's also very important to think about boundaries, so reservoir boundaries. This is probably the most simplistic model we can think about. It's just a single fracture a model that we're producing from, a so-called symmetry of element type of model. It only has one boundary, and that boundary is on the right and left side of the fracture. There's only flow in one direction. So we actually call this model a one-dimensional model because there's no volume beyond the frac tip. And if I show this in 3 dimension, you'll see that there's no volume beyond the frac height either. So there's only flow in one direction, and we call that a one-dimensional model. In terms of flow regimes, however, for this model, we can only observe 2 flow regimes. The first is infinite acting flow regime, which you'll observe until you actually feel or observe these boundary effects at the side here. And then it will be followed by boundary dominated flow. So in this case, for this very simplistic model, there will be no transitional flow, call it regime itself, because you're going straight from one boundary, or you know, you see all the boundaries at the exact same point in time. And that same principle applies actually even if you, let's say you assume that you have a whole well bore with these fractures. If they're all the same distance to the closest boundary, their so-called symmetry of element model, it's actually still only one boundary that's relevant because they hit the boundary at one point in time, so it's still a one-dimensional model. If we start to add a little bit of complexity, if we look at this reservoir model right here, which has basically 2 boundaries, it has a little bit of volume beyond the frac tip, and it has the boundary in between fractures or on the side of the model right here. So now we're dealing with a 2-dimensional model. We have flow in 2 directions. So this is a little bit more complex. And here we're actually dealing with 3 flow regimes: infinite acting, transitional flow, and boundary dominated flow. There's different ways of getting this sequence right here from infinite acting, transitional flow to boundary dominated flow. And now I probably know what you're thinking. You know, enough of these flow regimes already. I think we've got that at this point. But there's one more thing that is really important in this context. And the reason why we need to remind ourselves all the time is that a lot of the techniques that we're using, they have an inherent assumption of flow regimes. And when it comes to tight unconventionals, you can, if you think about these 3 different combinations of flow regimes, you can probably mix. I think I counted 7 different ways of sequencing this. These different flow regimes. So you can either have infinite acting flow for the entire observed history, or you can have infinite acting flow followed by transitional flow for the rest of the observed history, or you can have infinite acting flow followed by transitional flow, and then finally boundary dominated flow. Or you can have the case that I already showed, which is just infinite acting flow followed by boundary dominated flow. Or you can have transitional flow for the entire observed history. You haven't seen any boundaries or the final boundary yet. Or the second to last one is initial. You're skipping infinite acting flow. You straight see some boundary effects from day 1, and then it's followed by boundary dominated flow in the end. Or you actually are in full boundary dominated flow if you have a very modern completion, tight well spacing, very tight cluster spacing, a little bit higher perm regions. You might observe that in a little bit more digestible way. You can think about it like this. But this is kind of the sequencing that we're, you know, this is the world, potential world that our wells are living in in tight unconventionals, and now I'll not talk more about it. But it is really important to understand that sequencing of potential flow regimes that we might be subject to, and they can be very different in terms of how we develop our fields, but also the nature of the systems that we're developing as well. The second thing now is we're going to jump into RTA in a nutshell. So we will talk a little bit about different types of RTA, and I'll not go into the details now. I'll just give you kind of a brief taste of it. Then we're all going to do it well together. And then we're going to actually start up with the juice of the course a little bit more in detail. But I want to activate you all fairly quickly here. So the different types of RTA that we're dealing with is three different types. It is classical RTA, the square root of time plot. It's numerical RTA, which is the Bowie workflow we'll talk about, and it's the fractional RTA. And before we start to use these techniques in the software, it's important that we know kind of at least the basics of all the different techniques. So if we start with classical RTA, to understand that, you need to understand the square root of time plot. And the square root of time plot looks like this, and it has essentially two important lines. It's the slope through the data here, the black slope, and it's the time to end of linear flow. So important number one is the slope of this line. That is how we get our estimate of our LFP or our so-called A root K. And then the time to end of linear flow, that's what gives us the OIP. Okay, so if you take a look at what is plotted on the axis here, it's just the square root of time on the x-axis. That can be the material balance time typically, but it can also be regular time. And then on the y-axis, we're plotting something called rate and normalized pressure, or abbreviated RNP. But it's just the initial reservoir pressure minus the bottom pressure divided by the rate. And if you do that, you typically get this upward curve right here. When it comes to the slope, so the slope is inversely proportional to your LFP, which means that this is a small LFP, this is a big LFP, and this is an even bigger LFP. The time to end of linear flow is proportional to your pore volume. So this is your a small oil in place, this is a big oil in place, and this is an even bigger oil in place. So going back to those two slides that I talked about, flow regimes, and what we can derive from this analysis, the square root time plot, at least under ideal conditions, etc., they can in theory give us these two things that we're looking for. Number two is numerical RTA. And numerical RTA was introduced to solve one of the inherent problems with classical RTA. And the problems with classical RTA is that it assumes single phase flow. And when you derive reservoir parameters from it, you assume either a constant rate or a constant pressure solution. While in reality, we're dealing with both changing rates and changing pressures. That's what we call superposition effects. But in addition to that, we go below the saturation pressure in most of these wells. So the combination of what we define as multi-phase flow and superposition effects is what this numerical RTA technique is solving. So to dumb it down a little bit, if we have our square root of time plot, we plot the points above the bubble point. That gives us one slope. Then when we plot the points below the bubble point, we get a different slope. This different slope has nothing to do with boundary effects. So if we then pick a time to end of linear flow based on these apparent boundary effects, we actually end up with a too small of an oil in place. That will then lead to higher permeabilities, shorter fracture half lengths, and typically justifying more wells per section. And you all know the story from there. So what Braden came up with, and we'll talk much more about this technique later, but I want you all to use it as well, is a little bit different diagnostic plot than the square root of time plot, but it gives us the opportunity to quantify our A root K or LFP and our oil in place or gas in place with essentially running a numerical model in a systematic way. And the way that Bowie diagnostic plot looks like is what we see here, just LFPs versus time. This is as long as the line is horizontal and flat, it indicates infinite acting linear flow. Deviation below this line represents boundary dominated or transitional flow, and the magnitude of the line itself indicates the LFP. And if you like to think about time to end a linear flow, I guess that line would be somewhere in between here. And this is the technique from Braden on the picture here. The other thing you do, and we'll look at everything behind the hood a little bit later in the course, but the other thing we do here is to run the numerical models with different pore volume sizes. So we actually end up with getting not only the LFPs versus time, we also get a wide range of type curves. So we pick two things, the LFP, which is where we have a straight line portion of our data. Then we pick the second thing, which is the closest OIP stem, and that represents our contacted pore volume. Okay, so we pick two parameters, and these are the two parameters that we talked about in the introductory slides. Those were the two parameters that you can get from the square root of time plot, and it's also the stuff that you've been doing all along if you've been doing RTA in the past. Square root of time plot, LFP, time to end a linear flow, OIP. Okay, the inputs to numerical RTA is PBT, production data, and rel-perm. Relative permeabilities is not something we typically measure or can calculate from readily available data. So this data can be somewhat of a problem since it is an input, and that's why these guys in Cotera, or Cimarex at the time, created this multi-phase flow material balance technique that doesn't require relative permeabilities. So that's going to be the course for next month, and we'll not talk much about it here, but that can be used to constrain at least some of these parameters. The third thing I promised to talk about before we're actually going to run through a well is what we call fractional RTA. Fractional RTA solves an inherent problem with both classical RTA and numerical RTA. That problem is that all these models that we typically apply in the industry, they assume that the fractures are equally spaced. But as we've seen in many of the test sites, many of these ConocoPhillips papers, etc., we know that the reality is much more complex. Maybe it looks something like this, or maybe it looks something like this. This is kind of the fracture swarm concept that has been popularized through these Rademan papers from ConocoPhillips, where you have highly uneven frac spacing, but they're highly planar as well. So the difference between classical RTA and fractional RTA is that classical RTA solves for equally spaced fractures. So they give us an A root K. Okay, so that's just A K to the delta of 0.5. And then the fractional RTA solves for complex systems of fractures. So they give us the A K to the delta. So when the delta is 0.5, it's just a special case of a more generalized system. Okay. So when it comes to generalizing or resolving parameters, you're then resolving an LFP, where the LFP is your AK to the delta. Okay, and how do you quantify delta? You just plot your rate. You just plot your rate normalized pressure. Remember, that's exactly the same stuff we did for the classical RTA plot. The only difference is that we're not plotting it versus square root of time. We're plotting it on a log-log plot. And with that, we can just fit the power law through it, and all of you guys will do that in the course today. And this delta parameter right here is what is a value that should be between 0.5 and 0. Okay, so the physical significance of delta is if you're in infinite acting linear flow, then delta is 0.5. If you're in boundary dominated flow, at least if you plot in the material balance time, your delta is 0. And then if you're in transitional flow, then your delta is somewhere between 0 and 0.5. Okay, and all of this functionality is in Whitson Plus. The fractional RTA stuff is fairly new. We have the analytical diagnostic plots all ready, and we'll get the numerical versions that we'll talk a little bit about later here in the next release next month. So with that, I'm just going to ask if there's any questions. There's just no questions, but just a few folks that needed some help with Maybe we missed a few folks maybe in the setup. That should be fine. What we'll go ahead and do now is actually to go through this workflow all together, and we'll do that very kind of step by step wise for one well. So I'd like you to go into your project in Whitson Plus. So hope you've been able to log in to courses.whitson.com. When you see that, you'll see the fields view right here. What I like to do sometimes is to click F11, because F11 maximizes my screen, so I get a little bit more real estate. The second thing that I like to do is to reduce the zoom to something that is comfortable to me. I think the software suggests 80%, but probably somewhere between 80 to 67 for most engineering screens feel good. You know that you have a bad, if I can just show you an example, you don't have to do this, but I think you know that you have a bad zoom if a lot of the things are kind of moving into each other. So, you know, if you see here, for instance, where you can't see some of the units and stuff, you know that you should probably zoom out a little bit. So I like to use probably 75 or so. So that's two just introductory notes that I think is important. But in the view now, you should be able to see this field. We just call it the Permian. It's actually not Permian, but that's just to have one. And then we can go into our project. I see all the projects here. All of the projects should have 3 wells. You will only see the main project, and you'll only see the name of your project in the tool. And I think maybe Jordan Bowie, since I added you this morning, maybe Mo can help you get some wells into your project. Or you fixed it? Yeah, perfect. So just let Mo know if you don't have any wells in your project. If you click your project, so the way to click your project is just to be in the project view right here, and just click your project. It can be anywhere, and you'll see that you have 3 wells here. And we're gonna try to work with all 3. Maybe we'll just get the chance to work with 2, but we'll at least start with the first well being the kite well. And once you've done the kind of gone into your well, you'll be able to see at the top here that you should be in field Permian project, which should be your email or your name, and then your well should be, at least at first, is for kite well. Once you've done that, we should go to the PVT feature. We're going to start with the number 1 in the workflow, which is the PVT part. So yeah, and this is just a few tips. Use between 60 to 80% in your browser. Use either Chrome, Edge, or Firefox, not Explorer. You can use F11 to maximize the screen. And if you have any issues with what's happening on the screen, if you're clicking a button, especially now when we're like 40 people clicking the same type of buttons and we're using a cloud system, so you know if everyone clicks the same button, it might take a little bit of time sometimes. But if we're clicking the buttons and stuff does not update, for instance, then just do Control R or just do F5. That's exactly the same as just clicking this refresh button up here to the left. So that's a hard refresh. For many of you, there was a release last week, and you came to the software, and there was a few of you that you know, tried things and it kind of acted funny, and that was because you hadn't refreshed. So then the browser tried to be smart, and a lot of the stuff was stored in what we call cache. Okay, so just keep that in mind. And then the workflow that we'll go and do for this well is this 5-step workflow. We'll not spend a lot of time on step 1, 2, and 3, but we'll spend a little bit of time here in step number 4 and 5. So when it comes to the workflow, you know, the inputs are fairly easy, so it should be just to follow this menu to the left, and we're getting from A to C in the workflow. So when you're inside of your well, what I would like you to do is just to go to PVT here at the side, and just remember that you should be in your project and your well view. And then here, I'm pretty sure that most of you don't see the phase envelope. So to run that calculation, you need to go into reservoir fluid composition. that card. So this is something we call an input card. You click Edit Reservoir Fluid Composition. That's the same for all the input cards where the input is stored. That will have a own edit icon. The icon is the same in all the cards. If you click that edit icon, you'll get this box up. In this box, there is a wide range of different PBT methods. All of those methods we went through in the PBT course. The simplest method is the GOR method. That's the one that we're going to use now. In addition, now in the last release last week, we saw that there was a new feature where you can simply just drag this line up and down, and it provides you with a GOR pick that is based on your actual production data. And this is actually the same plot as for those of you who are seasoned that you see in the numerical view, just zoomed in by default to 100 days. For those of you who haven't used Whitson Plus that much, if you want to scale the axis here by typing, you go all the way up to the upper left or down to the lower right when your cursor is changing to this vertical arrow with an up and a down arrow. You click it. Let's say I want to change the maximum here to 2000. Just type 2000 and it scales. And just let Mo and I know if you want me to show this in the break. Anyways, what I would like all of you to do now is to take this line or type a number here, shouldn't matter, that fits this data and a value that you're happy with. Okay, so I'm happy with whatever I picked, but once you've done that, just click Save. Okay, and then you can also view this in cumulative space. You can also do this in OGR instead of GOR, but this is a low GOR fluid, so you should be good. Okay, so just let me know if folks have done that. That would be great. A thumbs up or something. I think there's like reactions now.
I think there's some people that are saying that their input box doesn't have the chart, Matthias. Maybe you can. So it has to. The GOR method has to be selected. I think that's the one thing.
Yeah. So I can go into. I think Chris. Yeah. I'll just check Chris as well. That's a good question. Yeah, that's not good, Mo. I don't know if the slide is down.
Checking with Jason here real quick. Just give me a sec.
Okay. Just while these guys are checking that, I can just go through the next steps here. So we'll go through step 1, 2, 3, 4, and 5, and if the data is not showing, that's obviously not a good thing. So maybe we need to supply a few more resources to make sure that it runs on the cloud. I think probably we broke it by running like 50 calculations at the same time. So that's a good thing. Anyways, so I'll just continue here in what we would like to work through. Mo, any comments?
Yeah, no, I was just saying that it seems like we need to just put some more resources to courses. That's it. But, we'll fix it and let you know as soon as possible. Okay, perfect.
So I think actually we can just continue. So I'll show from A to C the steps that we'll go through. Then we'll take a little break, and then hopefully after the break we've fixed it so we can do it together. If not, we'll just continue with some of the theory and we'll make sure that there's no more cloud computers available for calculation. But the thing in step number 1 is that we use this GOR feature, drag it up and down to make sure that we get a GOR that we're happy with. And what the software does is that it actually provides us with a prediction of the reservoir fluid, which you see here, based on the GOR that we've inputted, the surface process, and the equation of state for that particular field. That will honor the GOR inputs that we provided. And in this case, it predicts, of course, the solution GOR of 750 scuffs per barrel, a BO of 1.38, a bubble point around 2,900. And when we, I know that this is an undersaturated black oil, but you can also see that very clearly from the phase envelope right here. So we see the initial pressure and temperature is far above the two-phase region or the two-phase envelope. Okay. Step number 2, what we're going to go ahead and do here is we will not calculate the bottom hole pressures, but we'll just use the smoothing feature of the bottom hole pressures. That's a feature that allows us to take either calculated or imported data and just smooth that out graphically. These data points that we see here is just provided by SBE. So these, we'll assume that these are correct. That will just use the smoothed versions of these because we see there's a lot of spikes. And especially when we are running these numerical models, there can be a lot of issues related to running a numerical model with these kind of spikes in bottom hole pressures. So that's something we'll do in step number 2. And maybe I can just show if I store this in the cache. Yeah, so that will look something like this, and we'll go ahead and then smooth it, do an autofit, maybe add points if we need to do that as well, then make sure that we get something we're happy with. So that's step number 2. Step number 3, that's the course we're going to work with in the mid-August, which is the multi-phase flow material balance course. That will have a oil in place of around 700 MSDB, and we'll not spend much time on it. You can run it just to see that that's what it is in this case, and you can compare it to some of the values we're getting in our numerical RTA. Where we're going to spend the most time is to compare analytical and numerical RTA. And analytical and numerical RTA, the difference there, primarily, at least when you run analytical RTA on a single phase oil system versus numerical RTA that accounts for all the fluid systems, is that the LFP will be, of course, larger when you're accounting for all the different phases. So analytical RTA assumes single phase flow, while numerical RTA assumes multi-phase flow. So in general, you would expect the numerical RTA to be either equal to or kind of similar or higher than what we have in analytical RTA. The classical RTA plot, when you can use the autofit option, or you can try to fit it yourself on the screen when we get that, but you'll be able to most likely have something that's close to, and we'll add production data there, but that's close to 24,000. So that's again just the slope of this line right here. The inverse of that slope is basically what we have as our LFP. And the time to end linear flow is what gives us an OIP estimate. If we look at the fractional RTA plot, which we'll also do in the plot, we'll see that we'll have a early part of the data that gives us a delta of around 0.5. And then after a while, we get this period of a delta equal to 0, which is indicating boundary dominated flow. So here, this assumption of equally spaced fractures, etc., seems to work very, very well for this given well that we'll work on. Some of the later wells, we'll see that there's some difference to that. When we come to the numerical RTA step number 4, we will pick an LFP and an OIP estimate. That LFP and OIP estimate will be based on dragging this line up and down, and then either picking the OIP from the flow material balance, or just picking the OIP that's associated with the closest type curve here. Then we pick the two things that is important for our RTA exercise, the LFP, which is around 50,000 with the numerical RTA, and our oil in place, which is around 700,000 barrels. What's happening here early time? That is a good question beyond the scope of this course. If you want to know, check out this link for this YouTube video where Mo explains that in one of our previous knowledge sharing sessions. Yeah, when it comes to our RTA results here, we got an LFP that was around 24,000 in the analytical RTA view. Then in our numerical RTA view, we had around 50,000. So this is consistent with what we talked about before. And at least one thing that I think we've learned is when it comes to RTA, consistency is extremely important, especially in cases where you are uncertain on some of the input data. Once you've done your numerical RTA, you can just click export actually into a numerical model run. I'll see if I can just show that real quick here. So if you have your, might have to say that for later, but then we bring this into the numerical model history match. And then we see that if we have a good result in our RTA workflow, we'll get essentially a perfect history match on the first run in our numerical model that we can then bring in again and do a forecasting exercise on. In this case, we've then applied what we call a parametric decline here to the right. So this is just a history matching period plus the forecast. So with that, I think we'll take a 10-minute break. We'll be back at the hour, and then we'll just continue from there. Hey, Robert, we're just taking a break now for 10 minutes. We'll be back in 10.
Thanks.
Okay, so I'll just continue actually where we left off. We'll have to wait and get an update from Mo and the team there a little bit later once that is fixed. So apparently what happened was that we all clicked at the same time and we broke some kind of system. So it should be fixed here in a little bit. So we'll just continue on the theory part and then just do the actual hands-on exercises together when we get there. So then we'll do 2 wells just after each other after we're done with the theory. So what we'll go ahead and do now is just to go through all these 5 different steps that we talked about: the PVT part, the BHP calculations, the multi-phase FMB, the RTA piece, and also the simulation and forecasting. But we're going to take them and deep dive a little bit more into each and every one of them, especially the RTA part. But to understand RTA, you need to have some fundamentals related to PVT. And if this is the first time you're exposed to PVT, or if you have a limited experience with PVT, PVT is just a kind of a collection term for physical and thermodynamic properties of gas and oil. And we commonly refer to these essentially the phase and volumetric behavior of these fluid systems as PVT, pressure, volume, and temperature. And probably the simplest, call it PVT equation that you have been exposed to in the past is this ideal gas law, PV equal to nRT. So the question that many times comes up is what about water? So when it comes to PVT properties, then water is one of the things that there's not that much complex PVT behavior associated with that, but in some cases it can be important. But for most of these systems that we're dealing with, especially the complex PVT behavior, water is typically not important. So it's primarily the PVT properties of oil and gas that is really complex, and in a lot of unconventionals can be extremely complex actually for many of these fields. PVT models, being able to model PVT is extremely important because it's one of the few things that has an impact on essentially every single discipline in the petroleum domain. So PVT has an impact on reservoir, it has an impact on RTA and PTA and well testing, it has an impact on pipe flow and facility design, it has an impact on process and facility, reserves, and the list goes on and on and on. And it kind of makes sense because it's the way you try to call it model these, the way you try to model or what you're actually selling in the field is oil and gas itself. So to have a model to actually model what you're selling, kind of the entire business model of oil and gas companies make a lot of sense. The models that we're dealing with in any type of petroleum engineering related calculation, they need 2 fundamental properties for each phase. So this is the amount of each phase, the density of each phase, and the viscosity of each phase. Okay, so they need this for any type of calculation, and that's either described with a compositional model or a so-called black oil PVT model, which many times also in Whitson Plus and what we're going to talk about here, which is probably most in the industry today. Even all the tables that we typically use, they come from some kind of compositional or a so-called equational state model. So we'll just go in and learn what are the kind of the differences between these two on a very high level, because these are the type of models that we're going to feed into our analytical RTA, plasma pressures, flow material balance, numerical models, etc. So in a nutshell, to understand what an equation state model is, it is very helpful to start with the tank model. So if you believe that you have a tank and we define the pressure that is then gets exposed to the tank wall as force divided by area, that's the so-called pressure. Then we know that every time this particle, molecule, or atom or whatever is hitting the wall, it is then applying some kind of force or pressure on the wall. So if we have 4 balls in the tank, and we go ahead and, for instance, double the speed of these particles, then we see that we hit the wall more times. And that means that we're essentially increasing the temperature. If we then double the number of particles in the system, then we're essentially increasing the number of moles in the system. We see that we also hit the wall many times. So the pressure is increasing inside of the tank. So the molar amount is increasing. However, if we keep the same number of moles in the tank, but we increase the volume, we see that we hit the wall less times, and we can say that the pressure inside of the tank is decreasing. So with these fundamental relationships, way back, people that was probably way smarter than me, at least for sure, they realized that there's a relationship between pressure and temperature. They're correlated. Pressure and number of moles. And then we know that pressure and volume is inversely proportional. And that resulted in the ideal gas law, where the pressure is equal to the number of moles times this constant R, temperature divided by volume. And what the type of equations of state that we use in the industry today are just more complex versions of that. So the ideal gas law was introduced sometimes in the 1800s. Then we got the Van der Waals equation a little bit later, that I think was a Nobel Prize he got for that. And then we've made two types of petroleum engineering specific equation of state models to the oil and gas industry, the so-called SRK equation of state and the so-called Peng-Robinson equation of state. And these are the equations of state that was introduced in probably the 1970s, around that. They're at least when it comes to equation of state type of calculations in the oil and gas domain, those are the ones that are used 99.999% of the time. And in terms of predictive capabilities, they're very similar. Both are cubic equations of state, and you can use either of these equations of state in Whitson Plus, for instance. Fundamentally, what is an equation of state? It's just a model like anything else. That requires temperature, pressure as an input, in addition to composition. Composition is probably one of the things that are more abstract to us, so we can think about that as a GOR or a CGR. That's what it really is in a black oil sense. So when you have these different properties, you can then predict phase and volumetric behavior, saturation pressures, viscosities, compressibilities, formation volume factors, you name it. How does it look like? Well, when you've developed an equation of state, either of these equations, they're represented by two tables: component properties and binary interaction coefficients. So in any format that you give or send people, these are the formats that you'll typically be handed these over, if that makes sense. The equations of state that we're using typically in Whitson Plus are so-called basin-wide equations of state. So that is a process where we go in and take all the PVT data from all the wells in the basin, from all the different reports and from all the different laboratories, and create one field-wide equation of state that then can be used to predict phase and volumetric behavior for every single well across the acreage. So if you want to think about it a little bit simplistically, what I always say is that you can think about these equations of state for a field as a correlation that you can use for all fluid types that exists in that particular basin. And if you want to define it very kind of rigorously, we think about it as multi-sample equation of state models, where these two tables that I talked about earlier, they're fixed, but the composition, so the GOR, for instance, can change radically going into the model, and we'll be able to then predict the phase and volumetric behavior coming out on the back end there. So in this case, you're looking at one equation of state, and this is a black oil, this is an air critical system, and then this is a volatile oil. And if you really, really want to be rigorous about it, we say that each sample is described by one or the same EOS model, where each sample's unique composition is all that's required to accurately predict PVT data for that specific fluid. And the question that always comes up in kind of the aftermath of talking about this is like, okay, if this is possible, why isn't there one equation of state for all the fields in the world? We just use that. Well, in reality, the thing that we're dealing with is different fluid systems that has the same components up to C6, typically C1 to C6. Those components are well known. We can find their properties, molecular weights, etc., in any chemistry textbook. But if we take C15, for instance, if you measure that in the lab, a C15 is not a C15 because C15 can be made up by 1,800 different isomers. And what you're measuring is essentially just some kind of field average of C15. So a field average aromaticity or paraphenicity relationship is very correlatable to the thermodynamic or the PVT properties of that component. So for each of these individual basins, our job is to then to estimate these properties that are heavier than C7, which will be kind of field-specific component properties heavier than C7, typically going up to C30 or C36 plus. So when you have an equation of state, and what you will do in the software and what you automatically do in the software is just by providing very simplified input parameters, you can then go ahead and estimate your black oil PVT tables or your PVT tables in general. We know that PVT properties, as we talked about earlier, is a function of pressure, temperature, and composition. That's the fundamentals. That's exactly the same as the equation of state. Then if we think about that space, it's an extremely complicated space to think about because we have two components, we have two dimensions for pressure and temperature, and then we have n-1 dimensions for the number of components, where n is the number of components. So this is like in space that we can't really map out. But if we assume that the number of components is 2, then we're essentially dealing with the black oil model. That's what we're the most popular model that's probably used in all 99.9% of the petroleum engineering exercises we're dealing with. Very important to emphasize is that the black oil model can be used for all reservoir fluid systems, not only for black oils. And the question that always comes up in realm with that discussion is, why is it then called a black oil model? Well, it's just a tradition. And it is actually just a 2-component PVT model. And when the model was introduced, the oil in the tank, so back in the 60s or 50s, the oil in the tank was always black. There was not too many condensates, etc. And then you had the surface gas. It was called kind of the black oil model. But as Keith Coates said, which was one of the kind of the pioneers within reservoir simulation and compositional simulation, that probably a better name would be the 2-component PVT model, where you have 3 properties for each component in the table. So for each pressure, for instance, in the reservoir, you create a table at a constant temperature. Then you have a pressure column. Then you have the solution GOR, formation volume factor, and the viscosity for the oil. And then you have very similar the solution CGR, formation volume factor, and viscosity on the gas side. And this is the stuff we use for all the different types of simulations. Back in the days, we dealt with what's called traditional black oil tables. The problem with those tables back in the days was that they assumed that all the reservoir gas was dry, so that it didn't have any condensate in solution. And that is wrong, and there's still some software that use these tables, and it can be particularly dangerous for unconventionals, where we know that a lot of the condensates are actually, or a lot of the reservoir gases are holding a lot of condensate in solution, even for oil systems. And the reason why I say that is when you go below the bubble point and gas is coming out of solution, that gas that comes out of solution might actually be able to hold a lot of condensate in solution. So what we use are so-called modified black oil tables. That is what we use in the software. That is the thing that is recommended in general to use. It is rigorous on both sides of the critical point, if you like. It has 3 components for the oil and 3 components for the gas phase. And accounting for this RS term is actually also, it's more correct, but it's also better as well for economics, because you'll be able to, or you're actually, honoring that condensate that turns into liquid at surface many times. Very good. So that was short on PVT. We'll be even shorter on the next thing, which is bottom hole pressure. We had a huge long course about it in general. And what's important to know about PVT pressures in the software is that we have or support 4 different correlations. All of them are calculated at the same time. Beggs and Brills, Hagen and Brown, Polis-Meyer, Dengaillard, and Gray. Those are the 4 different correlations that we calculate in the software. you know, depending on what company you're in, what experience you have, maybe you compared measurements versus any of these correlations, you might have some preferences on which correlation to use. As we learned in the previous course, the main difference between them is how they estimate this liquid holdup term, which is what is primarily, you know, here, or, you know, early time here, you see that they're basically overlapping, and that's because it's a period of time where gas is not coming out of solution. But as more and more of this system becomes three-phase, you'll see that there's more and more of a discrepancy between the different predictions. But the reason why we always calculate all of them is just to communicate that potential uncertainty in the different correlations that we calculate. And then you can also cherry pick which of these you like to use for your simulation. We'll not go into any of the details here, but as we all know, measured bottom hole pressures is of course always better than calculated. But I would also say that calculated pressures are better than not having any pressures. There's multiple correlations also beyond the four that we mentioned and talked about here that can be used. But we know that the calculated pressures that we're using can be subject to a lot of noise that is just introduced by uncertainty in rates. A good example is a lot of noise introduced from water rates, for instance, at measurements of water rates at surface. You know, that's not a phase that we're selling, so we don't, or many times we're not too careful about the volumes that we're recording for water. Many times, as we also do in the software, is we allow you to automatically smooth the bottom hole pressures. So the smoothing might be required, or many times recommended, at least for numerical modeling. At least, so if you are running a model and your well control is on bottom hole pressure, then you would like to at least remove large spikes like these, which is definitely not a reservoir response. The reason for that is just that it will struggle to probably converge with, at least with complicated fluid systems and whatnot. First, we'll assume that the BHPs that we use are good, but we'll allow you to have some flexibility to then pick whatever correlation you like to use in the workflows that we'll walk through. The last thing that we'll kind of rush through a little bit is the multi-phase FMB. We mention it here for completeness, but again, back to this unconventional reservoir workflow, it's step number 3. The problem that this methodology is solving is that any multi-phase model, at least historically that was on the market, you had to have permeabilities as an input, but in reality, we don't have that. So in 2020, these two guys, Leslie Thompson and Barry Ruddock, they were at Coterra or Cimarex at the time, and they said they've developed this new method. We have tested that method. They've tested that method. Multiple of the companies in the audience have tested that method on both field data and simulated cases, simple cases, complicated cases, all kinds of rel perms, etc. And it provides us with the correct answer every single time. So also encourage you to try to find a case where it doesn't work, because I think Leslie and these guys are very interested in knowing about that. But we know this methodology works. It does not require relative permeabilities. It outputs our oil or gas in place. It does not care about geometry. It assumes boundary dominated flow, which means that if you're still infinite acting or transitional, you'll be then resolving a conservative oil in place or gas in place number. So in that case, you can then use it to bound your RTA analysis, especially the rel perm piece. Diagnostic plot is very simple. It's just plots on the line, and the inverse of this line is your pore volume. So this is a small OIP, this is a big one, and this is an even bigger one. And there are some nuances related to how you interpret the plot, etc., that will be covered in that follow-up course. And the governing equation, which is very much to digest the first time you see it, is actually fairly simple if you break it down. This is an intercept. This is just material balance time. This is your pore volume. This is the total mass rate. That's just like oil, gas, and water, the mass of that produced from a well added together. And this is something called mixture density change. So that's just the density of that entire mixture. So you just take the volume of oil, gas, and water divided by the mass, or the other way around. And if you look at this equation, if you actually apply mass rate on both sides, you actually end up with density is equal to mass over volume, which is something we know from one of the first things we learn about in high school. The other beauty is that it's a linear relationship, which is the dream of all us engineers, to be able to deal with something highly nonlinear like multi-phase flow material balance or multi-phase effects and superposition, PVT relationships, etc., and simplifying a lot of that complexity into a straight line relationship is really intriguing for many of us. So those were the three things we kind of had to, just for the completeness, cover the basic theory of it. But now we're going to take the step into the realm of RTA theory. And we'll go through the different things a little bit more in detail than what we did the first time. So we know some of the basics. We know there's a slope on the classical RTA plot. There's a time to end a linear flow curve. We know there's a delta from the fractional RTA, and we also know why we did the numerical RTA workflow, why it's needed. So that's step number 4 in this unconventional reservoir workflow. The reminder is what we can actually derive from RTA. Again, that's LFP and OIP, or OJIP, the pore volume. LFP, that correlates with 1-year CUMs, while oil in place correlate with EUR. Okay, so and sometimes LFP correlates with EUR because LFP correlates with OIP. Okay, and that makes sense. Like if you're having a larger, size job, and you're increasing your LFP, your average K, your area, K is whatever it is, then you're also increasing your OIP. So sometimes you can get these cross correlations, but you can have the same LFP in a wide range of oil in places, and the largest oil in place will always give the highest EUR. So just keep that in mind when we talk about these things. Again, LFP can just be observed during infinite acting linear flow, and then this can also be observed during boundary dominated flow. So when it comes to the LFP, what are the total area that we're talking about? What are the terms that makes up our LFP parameter or our average K? Well, it's 4 times the number of fractures times the half length times H times square root of K. So it's basically all of these guys right here that I'm plotting on the screen. The area of that. So we see that this guy is the square root of K. These guys right here, that's the area. And the question that we get many times is like, okay, I understand why this is an H, and I understand that we need to calculate the area of this, which is 2 times XF times H. And then I also understand that to get the entire area, I need to multiply with the number of fractures. But why is it 4 in front of this and not 2? The reason for that is that the flow into the fracture comes from both sides. So the total area available for flow is 2 times 2XF NFH. So that's where the 4 number comes from, for those that wonder about that. The second thing is this contacted pore volume in this box. What is the contacted pore volume? Well, it's that box that we're talking about here, the stimulated rock. Okay, and this is just a way to calculate it. It could be the pore volume, hydrocarbon pore volume, you name it, just different ways to quantify it. So those are the 2 things that we can quantify. And the different methods, classical RTA, numerical RTA, and fractional RTA, they have some different assumptions. So when it comes to comparing average Ks, at least if you're comparing them across these different methodologies, you should know the fundamental assumptions and their fundamental differences, and you should not expect them to be the same. Simple example is classical RTA assuming just single phase flow versus numerical, accounting for all the numerics and superposition, etc. The same goes for fractional. So just keep that in mind. So if you apply one of these techniques and you want to compare them to other wells, at least compare apple to apples. You can run them for all of them. There's a lot of information in all of them, but classical RTA, compare classical RTA to classical RTA, numerical RTA to numerical RTA, fractional RTA to fractional RTA, and just know if there's differences. Those differences should behave fairly consistently. So we'll start with the classical RTA, and the classical RTA is the first thing that we always learn about when it comes to RTA in general. The key assumption is a one-dimensional model, so-called symmetry of element model that we talked about before, which also means that there is only one no-flow boundary, and that no-flow boundary is between the fractures. So here we go directly from infinite acting to boundary dominated flow. This is also a fundamental assumption in numerical RTA, at least the current commercial version of that. And it's really important to understand the implications of this in reality. So again, that's the fundamental assumption. The plot, as we talked about before, just in a cartoon sense, this is how it looks like for an oil well, for instance, has probably three important things. The x-axis provides us with, typically is material balance time that we use there as a default time function. We'll talk about what material balance time is. The second thing is the y-axis, and from the y-axis we also, and what we plot on the y-axis, we also get the slope of this line. So the y-axis, that's where we plot the rate normalized pressure, and with this we get the slope m, and that slope for this line, that's where we get our A root K. And the last thing is the time to end a linear flow line. This time to end a linear flow line in dashed, that you'll see that in our software and other softwares, that you can move that around in all the plots, and that is either decreasing or increasing your pore volume, and it also changes the parameters that we're resolving in terms of fracture half length and the permeability. So we'll take all of these different pieces right here, and we'll try to just break them down one by one, starting with material balance time. Material balance time is actually also used a lot in fractional RTA, and is also used a lot in the flowing material balance. So it can be important to know at least the most important things related to material balance time. So material balance time is probably the most common thing that you, in terms of at least time series, that you apply in rate transient analysis. So it's very common to apply, and it's the default in Whitson Plus actually for these features, and I think it's probably what most of the other vendors also recommend. What many people don't realize or don't know is that material balance time is actually a superposition time function. So it accounts for changes in rates and pressure, and it then converts that variable rate data into an equivalent constant rate solution. So what does that mean? Well, it means that we then, at least in ideal conditions, can then use the constant rate solution equations to back out reservoir parameters. And that's what we're going to show here. That's what is discussed in our manual, etc. It's rigorously derived for boundary dominated flow. So there's theory, mathematics behind that it's a rigorous technique analytically. But it's also found from practical cases that it works very well for infinite acting data as well. But it should be noted that it's only an approximation. So errors can be up to 20%, but it works well. Mathematically, and that's probably the beauty of it, is extremely simple. It's just a cum until that point in time, divided by the rate at that point in time. But since your rates can go up and down a little bit, you can actually your time can move back and forward when you have real data. So for some, that can be a little bit tricky to deal with. The solutions when it comes to call it the slope, for instance, that I talked about, etc., for constant rate, they have been derived by very, very sharp folks many times in the past for linear flow, linear infinite acting flow. And we know that on the square root of time plot, if we plot rate normalized pressure versus square root of time, we should get a straight line on that plot as long as we are in infinite acting flow. And if we are in infinite acting flow, the data should follow this relationship right here. So this is the equation for oil, single phase oil, and then single phase gas. These guys right here, this is just a coefficient for field units. These guys are just PVT properties. And then you have porosity, permeability, XF, and H. That is more petrophysical parameters and completion parameters. For gas, it's a very similar type of equation. Just note that we're using pseudo pressure for gas instead of just regular pressure. And the definition of pseudo pressure you can find in the manual. These are the slopes. So when you have the data in Whitson Plus, for instance, you have drawn a slope through the data. You can use the slope to derive your LFP. And as you see here, 4 times H XF squared root of K, that's your LFP. So that's how you get that out. The second thing is the time to end a linear flow line. That there's also an equation for that, again, for constant rate. That has been published many times in the past as well. We simply just use this equation to solve for permeability, okay? And then we plug that back into the original equations for the slope. And then we get the product, which is A, the H times XF. And many times then we assume a certain H, but just with that, we're able to then come up with our estimate of pore volume. So time to end a linear flow gives us the permeability such that we can get a pore volume estimate. Okay, so we see that the larger our time to end a linear flow number is, the larger our pore volume will be. So that's how all these things are kind of interconnected also in Whitson Plus. The next topic is the numerical RTA. We'll take that one step forward now before we take a break, and then I think we do fractional RTA before we start some of the exercises. The numerical RTA is also step number 4 here. Just again, remind us the inputs here, PVT, production data, and rel perms. So that's where we typically use the multi-phase FMB to guide us a little bit on the rel perm choice. We exactly the same as with the analytical RTA. The fundamental assumption here is a one-dimensional model, only has one boundary. So LIST's original version of numerical RTA can only account for infinite acting to boundary dominated type of systems. We're and that's the same for all of these analytical techniques as well. If we think about the industry standard workflow that we talked about, the classical RTA plot, they work great when you're dealing with ideal conditions. So here we're dealing with single phase flow at constant bottom hole pressure. So we know that the constant bottom hole pressure is here in gray. It's above the bubble point, and this is a simulated case. And when we then plot the rate normalized pressure versus square root of time, we get a straight line on this plot. And from this line, as we talked about before, this is where we get our LFB. So yeah, constant slope while we're in infinite acting flow. However, when we start to introduce these superposition effects, which is just changing rates and pressures, that's where we then basically get into trouble when it comes to our square root of time plot. So instead of a straight line, even though it's the exact same well that we know is infinite acting for the entire time period, we see that we're getting a wide range of different slopes here in blue. That will probably all give us slightly different LFP estimates, even though the LFP for this well is given. And now we're not even we haven't even introduced multi-phase flow type of behavior. This is just pure superposition and superposition effects introduced by this changing bottom hole pressure profile instead of a constant one, still above the bubble point. If we make this even one slightly, at least a little bit more realistic, and we introduced introduce multi-phase flow effects and superposition effects by drawing the well below the bubble point, then we'll see, as soon as we hit the saturation pressure, we'll get a deviation from the straight line behavior on the square root of time plot. And just to demonstrate that, we have the exact same well. We know it's infinite acting in both cases, but now we're taking the well and we're drawing it below the saturation pressure here in case number A after almost 300 days and case number B after around 150 days. If we then superpose the square root of time plot now, we'll see that we get this deviation, which is just a result of multi-phase flow and superposition effects and has nothing to do with boundary effects. So the problem is if we pick time to end a linear flow here, just because of this, these apparent boundary effects, we will end up with what I mentioned before: higher permeabilities, shorter fracture half lengths, and more wells per section. So the solution to this is this Bowie workflow that we've slightly introduced in previously in the course, and I will also do an exercise with a little bit later. It has nothing to do with either of these Bowies, but it's just after Braden, which is also part of the Apache team that's in the Numerical RTA JIP. To understand, we've always already looked at the diagnostic plot, and we would like to be able to understand what's going on between or behind the hood. And to really understand numerical RTA or RTA in general, there are three fundamental relationships that is important to understand. Those three relationships is that for any two wells, as long as this LFP is the same, then the rate performance will be identical during infinite acting behavior. Okay. The second thing is that if the LFP to oil in place ratio or OJIP ratio is the same, then all the relative rates, so GOR and water cut, will be identical for all times, both infinite acting and boundary dominated. Okay, this is super important. So if I scale, if the ratio is the same and I just scale then the LFP up to the same value for two wells, such that I get the same LFP and OIP, the rate performance will be identical for all times. And that's why I'm saying, when it comes to what we can derive, we can only derive an LFP and an OIP. That's unique, but number of fractures, permeability, all of those other things are non-unique. But these two guys, they are unique, at least for this geometry. Okay. The question that always comes up is like, okay, yeah, but like I never look at two different wells. Because these relationships are true when you're, if the two wells have the same fluid initialization, the same rel perm set, and the same bottom of pressure versus time. The question that always comes up at that point is like, okay, what two wells actually have the same PBT and rel perm relationships, etc. And the answer to that is no wells have that. But that's why we're applying these relationships systematically, not on different wells, but on the same well. So we're then applying these relationships together with the numerical model so that we can do RTA on or with the numerical model. Just to remind ourselves that these things are true. So here we have the same LFP, but the oil in place is different. Case A, B, and C. Here, case A has the largest oil in place, case B has the medium oil in place, and then C has the lowest oil in place. And we see that has an impact on the EURs. So this is back to an example where the LFP is the same, but the oil in place is the same, and that is what dictates the difference in EUR. If the ratio is the same, the GOR is the same, and the water cuts are the same. So all the relative rates are the same for all times, both infinite acting and boundary dominated. And you see the slope of these curves right here. If I scaled them to the same LFP value, since the ratio is the same, I will get exactly the same performance for all points in time. So the same LFP and the same OIP will ensure the same ratio for infinite acting and boundary dominated. So it's beautiful in that or from that perspective. So with these fundamental relationships kind of defined and known, Braden, he came up with this 8-step workflow that is, of course, automated in Whitson Plus, and it does exactly these 8 steps behind the hood for us. The first is that it takes a numerical model that we know is large enough to behave infinite acting for the entirety of historical time. How do we know that? Well, that's just trial and error. But you know, after you've tried a few things, you know kind of what will always be infinite acting. Simplest way, create a very simple reservoir model, one frac with a very large distance to the closest boundary. Since you or I or whoever else created this model, we know exactly what area and permeability that we assigned to this model. So the LFP of this base model, the template model, is known. The second thing is that we run this infinite acting model on the well's actual measured bottom hole pressure history. And once we have that, we get a set of infinite acting model rates. Okay, so these are rates. This is how this well would perform if there was no boundary effects observed for this well. What we do is to calculate the ratio between what we observe in the field in terms of rates and these model rates, and we get a ratio versus time. This can be done either with the instantaneous rates or with the cumes if you want to reduce some noise. That gives you a ratio over time, and this ratio that you then multiply with the LFP in step 1. And that's how you generate the Bowie plot. That's the diagnostic plot that we're using. So this is like the equivalent to the square root of time plot for numerical RTA. A flat horizontal line indicates infinite acting flow. Deviation below this line represents boundary dominated or transitional flow. And the magnitude of the line indicates the LFP itself. So the last thing you just do is to repeat this exercise for smaller oil in place volumes. That will make sure that you get different type curves that will see boundary effects at an earlier and earlier time in space. So when you've then picked your LFP parameter and you don't overlay your type curves, you're simply picked an LFP and you picked an OIP. That's the 2 things you need to worry about. And you're done. So to summarize, as we went through earlier, straight line indicates infinite acting linear flow. Deviation below the line represents boundary dominated or transitional flow. And the magnitude of the flat line indicates the LFP itself. And we're picking basically 2 things, LFP and OIP. And to look at it, you know, the step 1, you have to input PBT and rel perms. So it's only when you update either PBT or rel perms or bottom hole pressures that you actually have to rerun the case. Elsewise, you just move the line up and down. Then you do your interpretation to pick an LFP and oil in place. And then if you would like to, you can assume your H, your number of fractures, etc., to resolve some of the physical parameters. That's the K and XF, for instance. And this is what is called the numerical RTA workflow. The beauty here is that we're already using a numerical model, so it's extremely fast to get a numerical reservoir simulation run. So if you're having a good match in your numerical RTA workflow, you'll get a very good match also in your reservoir simulation workflow. And just remember that this is the stuff that you've done all along with the square root of time plot. You're picking an LFP and you're picking an OIP. So here we'll go ahead and just take a 15-minute break, and then we'll get back here in 15 minutes and then continue with fractional RTA before we're going to dig into some exercises. Okay, so we're ready to get started again. The last part on the theory, at least on the RTA topic. So that's the fractional RTA piece. And in general, what we talked about earlier, the main problem with any type of classical RTA method, whether that's numerical or the analytical version of that, the square root of time plot, is that it assumes equally spaced fractures. So that is for both the numerical and analytical version. In reality, we're dealing with sometimes at least something that's a little bit more complex, where the boundaries are observed at different points in time, and this difference between, call it classical and fractional RTA in terms of what we resolve is that we in classical RTA resolve the A root K, while in fractional RTA from Acuna at Chevron we resolve the A K to the delta, where the delta of 0.5, as we mentioned before, is just a special case when we have this equally spaced fracture system. The generalized LFP then will just be AK to the delta. That's what we resolve in that or in the realm of that, and we can, from the rate normalized pressure plot, get this delta parameter, or the inverse exercise, which is the pressure normalized rate. We can get this delta parameter, where the delta is when it's 0.5, we're dealing with something that's infinite acting linear flow, and when we're dealing with boundary dominated flow, then delta is 0, and then a value in between these, then we're dealing with a delta that's between 0 and 0.5. So fairly easy to remember, at least the theoretical part. What we didn't go that much into detail of earlier is if you look at this particular plot and this equation right here, just as with the analytical RTA work that we've done in the past and showed earlier today, there is an analytical, call it equation for this power law relationship right here. And just as with the linear flow example, it's one equation for oil and one equation for gas. And these equations, they look very, very, call it difficult. But if we break it down, it's actually familiar stuff. So this is the slope for oil. If we plug in a delta of 0.5 here, we get a 19.927. And I'm pretty sure you've seen this before, and it's this classic that we showed just a few slides ago for classical RTA, and this is the reference for that in terms of slides. Okay, so for the simple case, it then simplifies to this part of the equation. Same for gas. If you plug in delta of 0.5, you get 208. Again, this is also familiar stuff. And we've seen this in the past as well, which would be this guy right here and the same reference. Okay, so it's just a more complicated version of, or a more generalized version of the equations that we're already using. A challenge to the audience, I think, kind of at least in this part of the joint industry project, that could be interesting to look at is to see if there's any, at least when you work with field data, if you can correlate this delta parameter to some completion practices. At least if you're dealing with a perfect world type of example, if you have a very high cluster efficiency, at least if the clusters are equally spaced, you should expect a delta of around 0.5. And if you have a poor cluster efficiency, you should expect a delta that's far from 0.5 from the get-go. So, or a lot of complexity. So that could be an interesting thing to see if any of the audience, when you apply this technique on one of y'all's wells, if that provides some insights to that. The thing that we worked a lot on the past year, and which has probably been one of the key outputs of the numerical RTA JIP, is how you can kind of marry fractional RTA and numerical RTA. And if we had a well that was in transitional flow for the entire observed history, so this kind of power law relationship, and we then applied the numerical RTA workflow in, for instance, Whitson Plus, what you would see is that you would then have these type of key diagnostic plots. You will have a LFP plot that's crossing a wide range of stems. None of the cum stems would actually fit your observed data very well, and you just see from a rate time perspective that your actual production data down here to the right, and any of these type curves, it's not the same call it shape of those data points. So what we've worked a lot on is how can we combine numerical RTA and fractional RTA in a very simplified manner. And what turned out, which is actually a very, very elegant call it outcome or takeaway, is that the only difference in terms of how we do the workflow is that we just define our LFP as the area times k to the delta, but except from that, the oil in place is exactly the same. So if we make these two adjustments and just keep in mind this very fundamental relationship that if LFP, OIP, and delta is the same, then the rate performance will be identical for all times. So that means that it's same production, or that you'll have the same production during infinite acting, transitional, and boundary dominated flow. So that is a nice, call it, addition to the numerical RTA workflow. And just to remind ourselves that this is true, this is just 3 different cases, case A, B, and C, all have the same delta parameter, but all the other parameters are different, but it also have the same oil in place. And as long as the LFP is the same and the oil in place is the same, and delta, then the rate performance, multi-phase, everything is exactly the same. What Acuna did, which is probably one of the most elegant things that at least I've seen, is how you can take a delta parameter, for instance, of 0.3, and say, okay, I would like to create a well performance of with a delta of 0.3 from X number of symmetry of element models, and the difference between these symmetry of element models is the distance to its closest boundary. So let's say I want to have a delta of 0.3, then Acuna provided us with a recipe, essentially, of how you could take symmetry of element models and provide a distribution of those that collectively adds up to a performance with a delta of 0.3. And if you think about it, like each individual symmetry of element model that you control on a bottom hole pressure, that has a delta. All the individual ones will have a delta of 0.5. It's just that this guy is, for instance, always infinite acting. This guy sees some boundary effect at some point in time. This guy sees this very early. This probably will go straight into boundary. But when you combine them together, the combined well response is not a delta of 0.5. It's something in between, which is back to this power law type of relationship. So the elegant part is that we've now taken PBT, we've taken production data, which is the input to numerical RTA, and we've just added one input, which is the delta, and we still, of course, have rel prims. But the beautiful thing here is that we can keep all the fundamental relationships the same. In numerical RTA, we just have a fractional RTA workflow that has this delta parameter as an additional input, and the delta comes from this diagnostic plot that we talked about earlier, and that we'll go ahead and hopefully get to test here in the software in not too long. And I can just show if this is yeah. So the fractional RTA plot is essentially this plot up here in fractional RTA, and the delta is like the output from that. So we'll talk about that a little bit more a little bit later. The absolute last step of the unconventional reservoir workflow would be to bring this into a numerical model. That's step number 5, the numerical model and forecasting. Once you've picked an LFP and an OIP, it's important to remember that LFP and OIP, there's like an infinite number of combinations of reservoir parameters that can give us that LFP and OIP. So one of those will always give the same well performance, but it will just simply be one realization of your RTA interpretation. So when it comes to the software, you pick a numerical RTA, LFP, and oil in place. So if you're in the numerical RTA workflow right here, the interpretations that you're doing is the LFP and oil in place guys up here to the left. But we can have different realizations based on what we assume in terms of number of fractures, maybe frac height, and also well lateral length. Okay, so all of these realizations are different. They all have the same LFP and OIP and original gas in place, but when you bring them into a numerical model exercise, they give exactly the same rate versus time performance. And that's what you do here when you click export in numerical RTA and you bring these into your numerical model right here. That no matter how I combine these parameters, the history match will be the same. It will also be a very good history match on the first run. The numerical engines that, behind the scenes here, when you're running a numerical workflow, you need to have a numerical engine running it. We have one in Whitson Plus, but in reality, as long as it's a full physics reservoir simulation engine, for instance, Eclipse, CMG IMAX, T-Navigator, Sensor, OPM Flow, you name it, you'll get exactly the same results. So this is full physics reservoir simulation models. We're not accounting for, or like we're not doing any tricks on pseudo pressure variables, etc., to make it fast. The results that you will be getting in this kind of workflow should be the same no matter which of these simulators that you're using. When you're in the numerical model view, there's a couple of things that's important. The first one is related to grid refinement. We made grid refinement extremely easy for our users, so you can simply just pick between a low, very high, medium, or very low, low, medium, and high. The difference there is that we're just adding more grid cells into the model. And behind the scenes, the actual grid is a mix of logarithmic and uniform gridding out in the numerical model. And important for those of you who are using numerical models is that numerical dispersion is always inherent in any type of computational numerical and simulation. And this is, reservoir simulation is just one example of that. And if your gridding is too sparse, it can cause some issues, and those issues can lead to results being less accurate. We say that the results have not converged. But in most of these cases, we see that even our very low and low is capturing the most important physics in all cases. If you're unsure, you can just simply create a medium case, or you're tested it with high. And if there's big differences there, which it should very seldom be, then you of course can do that instead. So when the simulation grids are coarse, the numerical dispersion is an undesirable simulation artifact. Any simulator, not any special for R, any numerical run will have this artifact. So we need to ensure that we have sufficient gridding to ensure that we have accurate results. But more grids, that makes a slower run. Hence, there's this very fine balance between accuracy and practicality. When it comes to the mix of the gridding here, so inside of the frac tip, in terms of Y direction, we have logarithmic gridding, and then uniform inside in terms of the X direction inside of the frac tip, but it's also a logarithmic gridding from the end of the frac end out. Okay, so and if you're including this volume beyond the frac tip here, we're dealing with a two-dimensional model, and then since there's a lot of call it fine flow effects happening here at the end of the frac tip here, it is more important to have finer grids in this region. The second thing when it comes to numerical models is that you have to choose which of the input parameters or time series data you would like to control your model on. In the software, you can pick typically between oil, gas, water, and bottom hole pressure. The numerical RTA workflow is assuming bottom hole pressures. So if you want to get exactly the same results as in numerical RTA, just pick the bottom hole pressure. Then you will ensure that you'll get exactly the same results as in your numerical model here. In this case, I've actually run it on a gas control, so you see my gas fit here is perfect. And it's just dictating to you what is known, what are we telling the simulator that we know, and what are we actually telling the simulator to estimate for us. And in this case, we're saying that we want to estimate our bottom hole pressure versus time and our oil rates versus time, but we say that our gas rates are known. Here, there's also a liquid option. That means that you can just say that I want to honor the total oil and water rate in my history match, and not only one of the phases at surface. So that's something you can pick even for a given realization, which ones you would like to control it at. Default in the software, we actually, when you bring the results in from numerical RTA here, and you bring those results into your numerical model grid by clicking this export button here to the top, you're by default controlling the well on gas. The reason for that is that the gas control, at least if you have good gas data, in general provides you with better looking history matching fits. I don't really know why. I think Bowie or Braden from Apache have some theories of why, but at least if you want to show it to someone, it's the one that provides you with probably the best looking ones, at least from empirical data. But in general, you should, it's the same model that you're running in all the cases, so you should get the same. If you're matching all the data very well, it shouldn't actually matter that much which of the phases you're controlling your model on. This is just an example where I control the well on oil rate control. That means that the oil rate is perfectly matched for all points in time. But then you see that, okay, here I probably haven't done a super good job on my history match, but there's some discrepancy on GORs and bottom hole pressures, etc. If I do the well control on gas rate, the gas is perfect. My water is at least okay late time. But now I see that there's some discrepancy on oil. If I use water and I don't inject water, the flowback water don't account for that, then you will actually expect very bad results. And even the model here is not prolific enough or productive enough to produce these phases. So controlling it on water is an option in the tool, and it's an option in all the simulators, but it tends to be not a very common way to run your models. The last one that is very popular is, of course, bottom hole pressure control. What you see here is that we're using a fairly spiky bottom hole pressure control, and small spikes in bottom hole pressure causes a lot of variation here, or a lot of spikes in the simulator rates. So that's why a lot of people like to smooth the rates out before, or the bottom hole pressures out before they control a numerical model on it. But this is exactly the same petrophysical properties, but it is just different realizations based on the different well controls. I think there's probably a so I see we have some questions here. Sorry about that. Didn't see them. So I guess the first one is from Gustavo. Let's assume that we have a well with 20 stages and 5 clusters, total 100 fractures. And if the delta is 0.25, what does that mean in terms of our effective number of fractures? At least if you have the assumption that 100% cluster efficiency would yield, at least for a period of time, a delta of 0.5, then I think you would probably just have to run some kind of model with essentially a frac or some fracs that are not homogeneous, and see what that would equate to. I'm a little bit unsure if you can solve that analytically, but that's some of the work that I think at least would be super interesting to do. So it at least would tell me that, okay, if that's my mental model, that my delta is 0.25, then I at least haven't been able to have a good fluid distribution, and also not a consistent cluster efficiency across the different fractures. Rashida has a question related to the simulation in the software, and the simulation is always done on a quarter symmetry model in Whitson Plus. The thing that you can do in the software is, if you want to, is to go up to the right here, click export, and export it to Eclipse, Sensor, CMG IMAX, OPM Flow, etc. And you could then go in and make a more complex version of that model if you want to in any of those softwares. So that's also very doable if you like to create something more complex. We're also dabbling with trying to create at least some simplified versions of multi-well models as well. And that will, of course, be a little bit more involved than just a quarter frac. But for numerical RTA and the software, the get-go is a quarter frac, but you can have multiple different layers and whatnot in the tool. The last piece related to numerical modeling is related to the forecasting piece. The forecasting piece is even if you have the perfect history match, even though you've done everything right and you have every single historical data matched, and you know exactly what your perm is, your fracture geometry, everything. Even then, you don't know what your forecast is, and I'll try to convince you on why. Because as this guy mentions, there's two kinds of forecasters: those who don't know, and those who don't know they don't know. I definitely would say we need to be humble here. So let's say we have this historical bottom pressure profile. Let's say that's correct. We've done everything correct until this point. We characterized the reservoir perfectly. But in the future, we need to provide a bottom hole pressure forecast. That bottom hole pressure forecast, to say that we will know exactly what that will be day by day going forward, all potential operational issues, workovers, frac hits, etc. For a given well, I think that is being a little bit probably naive. So, in this case, there could be an infinite number of ways to forecast this well out. So saying that we know it for sure is very hard to probably believe in. But here, I think consistency, saying that in this area, the bottom hole pressure should at some point reach 700 psia or 300 or 500, whatever it is, and then use a parametric decline until that point in time, and then forecast everything out to the same day makes a lot of sense. And this is just an example of how you add a well with an added forecast in the tool. And for those of you who haven't done that before in Whitson Plus, it's very easy to just you can either use a constant bottom hole pressure. That's just a constant from the end of history and out. But probably a more flexible and popular feature is to use the parametric decline, where you say, okay, I want my initial BHP to be 1361, and then my final BHP to be whatever, and then I can then simulate that out for 10,000 days, for instance, and then run that forecast. So that is that in a nutshell. Great. So now we're getting closer to running some of these worked examples together. So the game plan is to run the kite well and the crow well. And we've been a little bit, I don't know if we've been unlucky today or what it is, but we've been having some technical issues on the software side, which has been a little bit unfortunate. So we will just wait a little bit more with that, and I'll just show a couple of things that I wanted to cover anyways a little bit later in the course. The first thing is just related to a question that we get a lot, which is, I want to do automatic RTA on all the wells that I have in my company. So I would like to pick this slope on the square root of time plot automatically for all my wells. So I thought I could just show you how that is done in the software, just as a simple demo, before we run some of these worked examples together. And then the second thing that I wanted to show is a case related to when to justify use of a low fracture connectivity, and then running analytical RTA with total reservoir fluids instead of just single phase assumption. And if we have time, we can start to dig into some multi-layer models, how to build that, and maybe even a dry gas example there all the way in the end. And here it looks like even internal is not really working, so that is also a little bit unfortunate. But okay, I'll start with the low FCD type of case. So a low fracture connectivity system is something that in some basins we see that that's required almost for every single well to be able to get decent or very good history matching cases. So a very excellent example of that is many places on a Darko basin, a low fracture connectivity type of assumption is required to be able to get a decent fit. So that means that you would then try to change everything else in the numerical model, and it will be very hard to get very good history matching cases. And then just by changing probably only the low fracture connectivity, you get a very decent fit. The question is, in which cases should you, or what should you look for to see if there's actually evidence for including a lower fracture connectivity? So assuming that you have a fracture that is not infinitely conducted, that there's some kind of skin. And mathematically, what it means is that there's just an additional pressure drop between the matrix and the wellbore. Okay, that's what it is. So I'll be super interested in hearing a few of the thoughts from you all in the audience as well. But at least when it comes to two things that at least I always look for is the following two things. The first thing is if you plot the square root of time plot, like what we see here, and you have a very positive intercept on the square root of time plot. That means that's one way that typically it would suggest that a low fracture connectivity system might be required here to get good numerical model history matches. It can also mean that your initial pressure estimate is actually wrong. It could also mean that. But if you're comfortable with all these other parameters, such as initial pressure, then that could be one indication. If you have historical data where you see that you're getting production below the saturation pressure, where the GOR starts to increase, and that GOR behavior is linearly increasing. It's not shooting up when you go below the saturation pressure, but it's kind of steadily increasing, like what we see on the plot here. That can also be an indication of a low fracture connectivity system. And it will be also super cool to see if others have other ways to in the audience of when they justify a low FCD or not. At least what we do and what I always advocate is to not include it by default, but if there are a lot of things that suggest in terms of just these simple diagnostics that you should include or decrease your fracture connectivity, which in by default in the software I think is set to probably 1,000 if I'm not mistaken, then you take that down to 100 or 50 or 20, and maybe even lower. I think Steve Jones, he discusses this in his paper as well about the GOR performance, where in this case you see this GOR that's basically going below the saturation pressure and is then shooting up like this. And then when you have a low connectivity fracture, then you like what we see here, it can be a more gradually, steadily, linearly increasing type of GR performance as what I tried to make a cartoon of here. Has anyone else in the kind of the audience seen other ways to either justify or try to explain, or at least looking for some diagnostics in the data that justifies a low FCD? At least these are the kind of my two go-tos, I think. I think Jordan, you're on the line, right?
Yeah.
Perfect. Because at least many wells that we worked on in the Montney, we've seen that we've had to have a lower FCD to be able to get, it's at least a very easy thing to introduce into a model, a low fracture conductivity to get very good problem if you like. But have you seen something like, have you seen that work a lot or in your cases, or?
It's definitely area dependent. I'd say some of the other signatures, I guess, on the numerical RTA plots, if it's starting out at a low LFP but then rising early time as rates decline, that's a good indicator. And then also just kind of looking at the buildups, like if it really builds up fast early time and then flattens, that's typically what I'd consider low fracture conductivity, because you build up that pressure within the fracture rapidly. There's not a lot of volume. So kind of looking at the pressure profile on the numerical models, seeing how if the model's taking a lot longer for the pressure to build up when the well shut in than the actual well did, then that could be a sign to drop down your conductivity.
So basically, so that's two separate things. Like LFP, if that starts to, call it, shoot up and crawl up early before it, call it, stabilizes, that can be an indication, you said, and the second was related to the buildup. Yeah. Have you seen kind of this any of these two as well? Have you checked just the analytical RTA plots or the classical RTA plots and the same?
Yeah, for sure. That's probably the first look for it, and then if we see it on the analytical RTA, then it's just something to look for going forward. But usually all those indicators kind of coincide with each other.
Yeah, no, that's perfect. Yeah, great. I think that's the same. It's just like, I think these two, why I like these is that I don't have to even have started to run the numerical RTA workflows to kind of see, I kind of have a suspicion even when I look at this. And then if the numerical RTA things and running the simulations and whatnot gives either, more justification of it, is just very nice to see that consistency. So that is perfect. I probably should probably add that to the list as well. Any else on the call that has had to lower their FCD in their models to get good history matching fits? Okay, that's good. The second to the last thing that I just wanted to show real quick is related to these plots that we have shown earlier, these analytical RTA plots, for instance, these guys here. And what is done classically is that we use one face for this, like the either typically is oil for oil systems and gas for gas systems. What we've introduced now recently is the ability to also do this on a total reservoir rate or a total liquid rate. That's if it's important to account for all the water, or if you want to compare wells with very different fluids, total fluids, then you can do that. So I thought just to show that as one of the things as well here, just to get that communicated and kind of exemplify some of the main differences there and why it can be needed sometimes. Some of the, all the ways to resolve parameters, etc., is exactly the same. It's just that the stuff that we're plotting here, the actual data points, are all converted to reservoir conditions. So I'll just find a project here and just pull up this guy here. So here you see I have a case. This is how it is default. And if I run the autofit on this, this is my oil phase fit. And then, of course, this is done in material balance time, but I now have an option to, of course, do it on oil and gas. But then we have this liquid and total reservoir option as well. And how we calculate these reservoir rates is just PVT and bottom hole pressures, okay? Because we have all the PVT properties for all the phases, and then we just use material balance and these equations right here. This is just material balance and counting to get to reservoir barrels. And then on the so if I'm flipping to a total reservoir rate, for instance, you'll see that if I do the autofit again, my total LFP is increasing because now I'm dealing with both a total reservoir oil phase, but also the water. And here most of the stuff is single phase early time, or single phase oil, no gas coming out of solution. But if it was a lot of free gas flow in the reservoir as well, then it will account for some of that as well. Just note that it's even though it's quote unquote multi-phase, that we kind of combine all of them together to get that total reservoir rate, it's somewhat pseudo when it comes to resolving physical parameters. So use it primarily as kind of for diagnostic plot purposes. And we have the same for maybe I can pick another well for this that has a little bit more interesting slope, but for the fractional RTA plot as well, here we see an example with total reservoir fluids, and here we see another one for oil, and that was there we go. So that's one of the main things that I wanted to show here. Another thing with relationship to the numerical models in the software now, which has been a new thing that has been introduced, is the ability to run these numerical models multi-layer. So now you in the numerical RTA workflow, if I took these results out, maybe I locked in my, it looks like I locked in my oil in place here as well. And I export these guys out to my numerical model. I can then get I can start to add layers in my well data. So I'll just run this case right here, the history matching case, real quick. So this is just for the one layer model, and then I'll add some layers here later. But since I know that since I did my numerical RTA run, that worked very well. Like I know that in between the type curve of 660 and this one of 1.1, that's where my results kind of live or reside. I know that I'll be getting pretty decent history matching cases here on my first run in my numerical model. And we see this on pressure, we see this on rate, we see this on my CUMs, and also my CUM GORs. And that makes me feel good. The difference in water, I'm not too worried about because I'm matching the water phase, at least after most of the flowback water has been produced back. But let's say I would like to create a multi-layer model in this case. then the multi-layer model would then be to go into well and reservoir data. And I would like to then add a layer. So I'll do a simple example here, a 2-layer model. And let's say I would like to ensure that I get very similar history matching results even with a 2-layer model. For instance, our friends in the Bakken, which likes to have probably 3 or at least 4 layers, they can add 4 layers here. But as long as I get this compound, call it permeability here, the layer weighted permeability to be fairly similar, I would get very similar history matching results as well. So here I know I have a total height of 56, so I'll just make this 26 and 26. And then I have a perm of around 57 that I would like to match. So I'll do something around 120, and that's around 60. Then I'll just keep the porosity the same in both layers, just for example purposes, and make them both fractured layers. And then if I click save, I now gone from a single well model to a 2-layer model. But I know that I'll get very, very good results in my first case also here, because my perm, basically my LFP, should be and is very, very close in these examples here. So we see basically the same history match, very close. Maybe I can tweak it a little bit on the oil sites, maybe slightly higher productivity. But here I could also go in and add different water saturations in my different layers, even different PVT properties if I like to do that, while honoring my my LFPs and oil in place numbers from Numerical RTA. You can also see it here in the saturation view here as well, that we have 2 layers with slightly different permeability. So we see the way it depletes, at least this is from like a gun barrel view, is somewhat different. Okay, so that was that low FCD, and also the so low FCD and the multi-layer thing was 2 things that I just wanted to show everyone. The last thing is this the opportunity to do auto fitting of all these wells at the same time. So auto fitting them from an analytical RTA perspective. You can do that by going into well by well, and you can do you can pick the face, and you can do. This actually doesn't have any oil, so maybe I'll have to pick a well with actual oil rates. Is typically a good example. So if this was not a good fit initially, and you click auto fit, it should provide us with an okay fit, especially on the LFP side. But this is kind of tedious if I want to go down here and do this for every single well. So this one probably is a gas well as well. So, but if I wanted to do this in bulk mode, that's possible to do as well in the software now. And the nice thing about it is that since we're like all these buttons are so-called API endpoints, so this can be automated for all of you that have a so-called API connection, such that you actually can go into a tool, open every single well, the last production data is from yesterday, all the bottom pressures are calculated until today, your LFPs are even calculated automatically. And if you want to run them in bulk, you simply go to the well view right here, select all the wells, click run selected, and then whether you want to do it for classical or fractional RTA, you just click here, classical RTA autofit, click the primary face, then you just do this on all these wells, and this is a way for you to then autofit all of these at the same time. So that's something that I know a lot of, at least a few of you asked that for, just to cover how that's done as a part of the course. Since let me just double check it for a couple of things here. Yeah. Yeah. So I think we'll take another break here at for 15 minutes, and then in the last hour, unless we've made sure that the software works again, I'll just actually go through those 3 examples together with you all to show how it is, and then we'll just take it from there. So we'll meet again at around the hour. Okay, it's 15 minutes from now. Okay, everyone. So we'll give this a last try on the running the cases, and if not, all other domains seems to work fine, but apparently courses is not our friend. So we'll try that. If not, I'll just go ahead and demo some of the cases for you. And then if you have an interest in just running through some of this on one of your old wells on your own domain or these wells, just feel free to reach out to me and we'll set that up. So what we'll go ahead and do now is that we'll go to this kite well, which is the first well, I believe, in your acreage, or in your project, where I think things crashed earlier. So let's just cross our fingers now. I think things should be good. So we'll start with this workflow, step 1, 2, 3, 4, and 5, and we'll do the step number 1, which is the GOR piece. So in your project, you should be able to find the well called Kite, and once you're in this view right here, called the PVT view, unless you have a face envelope here already, just open that reservoir fluid composition input card here and change this GOR to whatever you want, and then click Save. I saw there were some questions. Yeah, actually, yeah. So are people able to run this now, or to talk to?
Hello?
Yeah, hey Ma.
Hey.
So there we go. So folks got to this point now with just a thumbs up, or so you be in your project, your field, and your well, and under PVT, just go here, change the GOR to whatever you like, and then click Save. Okay, mine's working. That's a good start. That's how it should be. And then, so that's step number 1. We see from this that this is a undersaturated black oil. We see the initial properties created here at initial conditions. We can, of course, view this table graphically or in a tabular format, export to any third-party tools. But we know the engine that has been running behind the scenes is this equation of state model. This is just a default equation of state model in the tool, not tuned to any particular type of data. But that's just for example purposes in this case. The next thing that we'll go ahead and do that is a part of the workflow that we saw here in the previous slide is bottom hole pressures. That's all the way down here to the left of the menu. We just follow the menu down. So that's where we combine PVT and production data to calculate our bottom hole pressures. And I know what you think, Mal, but this is like not how it's usually was working, but Mo, are you there?
Sorry? Yes, Matthias?
I don't think it's there's something that is not really making it extremely slow, at least.
Yeah, I'm not sure.
Okay, so I think I'll just actually have to go and just show the workflow here on this domain, and then just apologize for that. And if you like to have a session on it, we can have it a one-on-one session on that as a follow-up. But step number 2, at least, is the bottom hole pressures. That's just a functionality that where you import your deviation survey. You define your perforated interval, and then if you have one or multiple wellbore configurations over time, you can then input that as well. Or you can mass upload it through a API connection or a database connection. The The thing that we typically do here in step number 2, it's to smooth out the bottom pressures if needed. So then you can do that on any of the calculated values, or you can do that on the measured values. If you do that on the measured values, for instance, or I can do the Bold, Smart, and Gaillard here, you can either start to just type them from just on the graph right here, as you like, or you can use the AutoFit function right here and then smooth out the data. Change the sampling frequency if you like to have more sampling data points, and then where you feel that you need some more fill-in, you can just fill that in. If you need to remove a data point, just drag that south of the y-axis here. Sorry. So there's multiple ways to delete this data. Okay, so if you want to delete this data point, just drag it down here. When you're happy with it, then you can just simply click Save. I had a set of data that I was already happy with. I'd smoothed that to the gauge pressures in this case. And you can see that in this overview right here. The third step is the flowing material balance. That's when I have my PVT and I have my bottom pressures. I can then run my flowing material balance. My flowing material balance in this case gave me an oil in place of around 700 barrels, or 700,000 barrels. That's just the inverse of the slope right here. So we see when I move the slope and make it less steep, that's a higher oil in place. And then if I make it steeper, it becomes a smaller oil in place. It's just an inverse relationship to that. And I would like to make sure that I have a slope that honors my data, but also, probably more importantly, has an average reservoir pressure that's always above my bottom pressures. I think around 725 gives me that slope in this case. So that's what I'm going to go ahead and use. When it comes to my third step, my analytical RTA and numerical RTA, that involves 2 steps. So you see here under analytical RTA, there is 2 different options, the classical and fractional RTA. The classical RTA is that's all the classical stuff we talked about before. If I move this line here, you see that if I move it more to the right, the time to a linear flow curve, that changes my oil in place estimate. It doesn't affect my A root K estimate. But if I make this less steep, my LFP goes down. If I make it more steep, my LFP goes up, and if I make it less steep, it goes down. And then I can use this AutoFit functionality right here as well. And I'll go ahead and answer a few of these questions just after this quick demo. For those of you who, from last week, we had a new release of the software. That's where we have the fractional RTA piece right here. So that's the fractional RTA plot. That's just material balance time versus rate normalized pressure. Here we see a slope with a delta of 0.5. That's what we talked about that indicates linear flow. If I make this 0, that means that we're in boundary dominated flow, and at least on this oil phase, it looks like we're getting into boundary dominated flow late time here with a slope of 0. So that's nice in that case, that you feel good of just using numerical RTA as this, and that some of the other things we'll see here a little bit forward makes sense. The next step is, of course, running the numerical RTA method. We talked about what's the inputs to numerical RTA is PVT, production data, and its relative permeabilities. Here we've made the relative permeabilities in the matrix slightly different from the default Corey parameters, but everything else is just the same as what is in that SBE dataset. So this is SBE dataset walls that we're just applying and using. What you can do in terms of your LFP and whatnot is to either type it in here or you can drag this line up and down. And you see when I drag this line up and down, my LFP is changing. if I had not locked in my oil in place, what the software goes in and does is that it automatically picks the OIP stem that's closest to my production data. So, but in this case, I wanted to honor my LFP, my oil in place for my flow material balance. So I said, okay, no matter what it is, I'm going to make sure that my oil in place is 270 or 725, such that when I change it, like now it's a little bit annoying that it changed to 975. So I want this to be 725, and I want to lock it in. And then when I change the LFP, my oil in place or gas in place doesn't change. And then I also see that here I'm getting some kind of pore volume between 670 and 1100. So that's in the ballpark of 725 as well, which makes me feel good. Here we might like to maybe do a little bit of things on my GORs, maybe reduce them a little bit so I can maybe increase my NGs a little bit. But at least so the only times that I have to change or rerun the actual method is if I change my rel perms or my PVT or things such as the pressure dependent permeability or fracture connectivity. And then you simply just rerun the cases and your interpretation technique is still the same. You just drag this line up and down to find a LFP that makes more or less sense and an OIP that makes sense. And you've done your job when it comes to the numerical RTA workflow. When it says that we're picking and running 5 different type curves, that means that we're running 5 different simulation models in the cloud at the same time. If I picked 10, it will give you 10 type curves, and these with the smaller and larger models, that's just indicating whether we want them to, on a relative basis, be going into boundary and see boundary effects sooner rather than later. I can also lock in my LFP here if I want this to be 50. What that will essentially do is that it, when I rerun, it won't automatically auto-fit it again. And it will also disable this opportunity to move this line up and down. But yeah, the last thing is that when you do this interpretation, you typically use a lot of the plots at the same time, not only the Bowie plot, but you want to make sure that your water cuts are decent, you're controlling it on bottom hole pressure, so you would like that to, of course, look consistent for all the cases. But probably more or equally at least as important is these type curves, that you can see that your type curves make, or the cube curves look more or less matching your historical data. So I know that if I bring this result now into my numerical model and I run it, I will get very, very good results. And maybe I would like to kiss this curve right there, or maybe not, something in between here. And then I click export. Then I export this into my numerical model. And then I know that since I did a good job on my first run, I will get very good results on my first run of this model as well. Yeah. Okay, so I'll go ahead and answer a few of the some reason. And also some of the questions in the chat, I'll just take those now when we're at it here. So the Rohit asked about is the numerical RTA workflow done on a single layer, or is there a multi-layer option for that as well? So as of right now, it is done on a single layer, but I think it should be fairly doable to include something similar to what we have right here, which is the multi-layer model that we're running right here. So I think that is something we can do in the future fairly easily. The only thing I think the height. I'm just a little bit curious what we'll do on the permeability part of that, but having some permeability contrast maybe between the layers instead of an actual perm number would probably make sense. But I think so. If it's only porosity and saturations and whatnot that you change, that can be a little bit something to discuss. But I think that should be doable. Kind of the workaround now is to do what I showed earlier, where you kind of match this weighted perm that you resolved from your analysis previously. And Gustavo also mentioned that the automation section will save significant time, and I think that's true in general. This ability to run all of these in a bulk mode, but also be able to do them with an API connection or a database connection, such that we can just run a single line of code every single day to update these, or to do it once you've already uploaded the data. Well, obviously provides a lot of savings when it comes to time, I guess. And Jonah asked a question related to, is there a way to link this analysis data back to some BI tool? All this data, like there's probably said that we shouldn't, not planning to discuss that too much, but of course that is a thing we get a lot of questions about. So there's 3 ways to connect to the software, in addition to, of course, using the front end. So use an API connection, so use a direct database connection, and it's to connect to, for instance, Snowflake. And all of those connections allow you to push and pull data back and forward to either internal databases or internal systems. So you can then connect that to, Spotfire or any BI tool as well internally, if you like to do that. And then Jordan also talked about this. That one of the things we're studying in the numerical JIP is the ability to do numerical RTA with multi layers, and that I'm pretty sure that should be possible to do. Also adding frac volume beyond the frac tips and frac heights is something that should be possible to already generalize for in the numerical RTA step. The Farshad has a great question related to linear superposition time as an alternative to material balance time. That is very easy for us to do. Very few people recommend to use it. Right now we have real time and material balance time. So I would, if that's interesting for you, Farshad, and if you have some strong, then of course we can implement that as a third option. It should be really easy to do. So just feel free to follow up on that. Manuel had a very good question related to the numerical model, and in the multi-layer version of that, if each layer has its own rel perm set, and the answer to that is that the rel perms in all the models or in all the layers are the same as right now. But I think probably 10 of the companies or so have asked if we can have different rel perm sets in the different layers if we want to. So I'm pretty certain that we in the near future will allow people to also add a rel perm set that is unique to every layer as well, if that's something they want. And I assume maybe, Manuel, that you would like to see that, or was that plus one? That's good too. Yeah, exactly.
That would be nice.
Yeah.
And while I'm at it, what about the vertical communication between the layers? Any sort of ability to change that, or is it just the permeabilities of the layers themselves?
Yeah, so there's by default now there's no vertical communication between the layers, unless I've been informed wrong there. Maybe Mo can add a cent or two on that, but that could be also interesting to look at, Manuel, if to have something that is not zero connectivity. That's what you're looking for, right?
Yeah, yeah. I'm thinking of a situation where you see first the signal of a really permeable rock, and then there's the other rock which is not as permeable, but eventually it'll start showing its signal later, but only when the first one is depleted. So
yeah, that's the issue that I've seen in the past with that is that it's been kind of tricky to get it to run. We can create a lot of numerical curiosity or like things with the model that makes it kind of funny, but that is and I know we have it in the backlog. It's just a priority item, I guess. At least going back a little bit to this, I just want to follow up on a couple of these things while we were at this part, because a lot of the questions was related to the numerical model. Once you have the history matching case, this is again just one realization. I'm controlled on gas rate in this case, and if you like to add a forecast, there's different ways to add a forecast in the tool. So you would then either constant or parametric, as I talked about before. And in this case, we're using the parametric from the end of history out to 10,000 days. Then you can just go ahead and run this as any other model. So it's controlling gas rate until the end of historical time. And then after that, we're running it on a bottom hole pressure type of constraint. And that's the same as we'll go ahead and do with this other well that we're going to look at now in a sec as well. The next step that the next well that I thought we could take a look at is this Crow well. The Crow well is the Crow well is one of the other SB data repository wells. It's very similar in terms of what you would do in terms of the steps A 1 to 5. This was one of the wells I actually wanted you all to just run yourselves to be able to do your own interpretations when it comes to the GOR. What should the GOR be based on this early production data? You have some very early production data here that's like 400 or 500, but it kind of stabilizes here before we go. Before we see that probably below the saturation pressure, it starts to shoot up here late time. So maybe here I would pick something close to 600 and save it.
Yes, I just think it's a quick comment there that if people want to try to follow, I think some people are actually running calculations. I can see that on courses. So you can just continue doing it on internal yourself, and then if people want to try to follow on courses, can try to do that. And if there's any issues, just let me know.
Yeah.
Sorry for the inconvenience there.
Yeah. So that's just the second well in the project here. So that's the Crow well over here. And then once you found a reservoir composition that you like, then you know that the software has then predicted a fluid composition for you. It has done that based on the assumption of surface process, GOR, and that equation of state in the background. And it's using that PVT data together with the production data that, of course, you can append to and upload and change as you like. This is basically now working as more or less as Excel. And then the second step that we mentioned in the workflow is to do the bottom hole pressure calculations. Right now, what you see in the front end here is just the measured data. If you click the calculate bottom hole pressures, that will go ahead and calculate the pressures for you. But you can also take a look at the inputted data for these particular wells here by clicking the well data card. We made a few changes to that last week, but the well deviation survey is still the same, top perforation and bottom perforation, and this is the deviation survey. So that with a perforated interval, then the wellbore configuration in this case is 2 versus time. We're first having a wellbore configuration where we're just producing through tubing without any artificial lift. And then after a period of time, we're turning on the artificial lift in end of January 2020. And then the valves, in this case, it's only one valve, but if you actually have all the gas lift tally valves, you can just import those and input those versus depth and use those in the calculation. And then the software automatically accounts for or estimates which of the wells are taking fluids at any given point in time. So that's the information, that's the rudimentary information you need to do the calculations. For those of you who are running like different types of lifts, for instance, we were supporting casing, tubing, annulus, flow. If you have co-flow through tubing and annulus, we can do that. If you have measured gauge pressures, for instance, from an ESP, we can convert the measured gauge pressures from the gauge down to sound phase. And also, of course, we support different types of artificial lift. So if you have ESP, then we can account for that as well, as I mentioned, rod pump, plunger, gas lift, or if you just have regular flow. Again, here on the once you're in this view, if you pick in this option here at the top, you can pick the bottom hole pressure to be used in a calculation. The bottom hole pressure is one of these, all the way up to either ones that are calculated, or you can click custom. In custom, you can then click edit custom BHP. The nice thing here is that you can smooth the data, as I talked about, and I've already done some of that here. If you want to remove a point, you just remove that down for the or south of the x-axis, if you like. And here I'm just making kind of like an artificial little build-up, but this functionality is very nice just to make sure, at least in cases where these spikes, for instance, are definitely not, at least I don't think, a real reservoir responses. So there's probably related to some water rates or something. So we can click save here, and then you actually can go ahead and use this particular smoothed BHP in your analysis. And that's what we're going to go ahead and do now. You also see that your reservoir pressure here is possible to edit in this view, and that's just because many times we would like to edit bottom hole or reservoir pressure based on the early time estimates of our bottom hole pressures. So that's something that is, of course, relevant for those who use that technique for initial reservoir pressure. Once we've done PVT and bottom hole pressure calculations and picked which of these you would like to use, now I picked just the fitted one to the custom or to the imported data, the measured data, but maybe I'll do the Voldesmeier and Gaillard instead, then just add my little artificial build up here, something like this maybe, and then go ahead and I can run my multi-phase flow material balance. I'll not actually spend too much time on this and this at this point in time, but so I'll jump straight to my analytical RTA. My analytical RTA I think was already auto-fitted, but let's say it was as something random like this, and I click auto-fit, then there is a algorithm that picks an LFP for me automatically, and time to nonlinear flow. And if I'm not happy with this, of course I can change these as I like. And as we talked about before, I can also do this on different phases. Same for fractional RTA. Now I see that this is not a delta of 0.5, and I would like this to be auto-fitted to my data. And I see it looks like I have a delta of at least auto-fit 0.39, but maybe I'd like to change this even a little bit more, getting 0.35 or so. So, you know, this might suggest that we have considerable heterogeneity here, and as I talked about as a little challenge to the audience, getting this delta parameter quantified for different wells and trying to link that to completion practices could be super interesting. My next step is to run my numerical RTA model. In my numerical RTA model, simply just change my relative permeabilities, make sure that I'm happy with my fluid inicizations, water saturations, etc., and some of the petrophysical parameters, and then I just click run. What you see that I've done here is to pick a small, like 5 smaller models. These five smaller models are picked to just get a earlier departure from a straight line trend, just because the data is kind of suggesting that to some degree. And if I want to make further changes, I can of course do that. I think even I changed probably some of my data here, but I'll go ahead and take this, export this into my numerical model, and then click run. And I think I can just go ahead here and make sure that I try to match my GORs a little bit better. So I can do a 2 maybe on my, or I can make this 1.5 as well. So once I'm happy here with my fit, maybe I want to change this a little bit. But I know, for instance, here I updated my flowing bottom pressures, so I can go ahead and rerun my numerical RTA, bring those results into my numerical model again once I've found something that I think makes sense for my data. Now you see I made changes in my bottom hole pressure, so that impacted my GORs a little bit. So I can then go ahead and make my NGs probably around 2 or so. Just rerun the models again, see if I can find a LFP and OIP that matches my case, and bring these into my numerical model. And in this case, the closest one is an OIP of around 1600. So I'll go ahead and export these results into my numerical model, click run, and then maybe add a forecast here if I want to make it even better. But I think we should have a pretty decent fit here for both oil and gas, and also the GORs. So the last thing we can do then is to go in and add a forecast from the end of history and out. So the forecast is added here again. You just toggle this include forecast option. And then you can just click edit BHP forecast. And I like to add a parametric decline, make that go down to 500 or whatever you pick yourself. I typically forecast it out for 10,000 days, and then you typically like this decline to be fairly similar to what it was before, the BHP decline before you start to do the forecast. And you can do this in terms of a hyperbolic function, or you can make it a linear one. So you can make it a pressure decline in terms of PSI per day. So that will make it like a linear decline. So if I make it 2, maybe that, so you see that's a linear pressure decline down to 500 in this case, if you would like to do that instead of having a hyperbolic type of function. So that's a great question from Amy. Are most people using BHP control when they have gauge data, and gas oil rate when they don't? I think that's a good way to summarize it. Like, if you actually have measured gauge data and you have a very big certainty in that data that is also correctly converted down to cent phase, there's probably no reason to assume that is a wrong measurement. So that's my general observation as well. But maybe there's some in the audience here that have different preferences. I know some of the audience, companies in the audience, like to probably run gas rate control no matter what. The nice thing, however, is that if you have a very, very solid fit, you'll get a very good match or history matching case no matter which of the rates you're controlling it at. But I don't know if Braden is here today, but is that like Jordan, for instance, when you've run these cases, is that you have 2 cents on that? Maybe Mo has a couple of.
Yeah, no. So I think I would agree to what Amy said as well. You have if you have a good, also if you, as you said, Matthias, if you have a good match on BHP control, then you should expect a good match on gas rates. The one thing that I see more than just having the data is sometimes it's also about which of the data you have that is fluctuating. So let's say you don't have bottom of pressure data, have oil and gas rates, but you see that there's definitely something fishy with your gas rates, then you just go and control it on oil rates, even though that's not the preferred choice in most of the cases. So trying to kind of honor the data that you think is most reliable is what most people are doing.
Yeah. And then the same goes like even if you don't have gauge data, maybe sometimes you have very periods of very fishy gas or oil rates, and you don't want to honor that. Then it's just trying to use the data that you trust more versus the other. So I think that's a good way to summarize it. Any other questions here, or?
I can see that quite a few have been doing the calculations at least, and all the way to the numerical model, so that's good to see.
Yeah, perfect. Yeah, I can show a few other couple of things here just for those. So of course, when you run the forecast, you can click hide forecast and include forecast just in the plot, so you can see it with and without the forecast. If you are into, let's say, here you can do kind of different sensitivities manually. If there's one parameter that you like to study, then you actually can go in here and then click basically this guy right here and say, I want to look at sensitivities for my matrix perm or my matrix porosity or my Corey exponent, etc. And then define those cases and then bulk run those cases here in the software, and then plot them all at the same time. It's actually done here, an example of that, so I'll just show that real quick. Maybe for 300, 400 days. So this is different cases for just a well lateral length. We just looked at a few different things, but then you can study things and how boundaries have an effect on your GOR ratio, for instance, or your gas oil ratio. Probabilistics is the last tab here at the top if you like to run probabilistics on some of your parameters. So if you define a subset of your parameters here, you can then go ahead and provide them with a distribution, uniform, triangular, or normal. And then once let's say you want to make fracture height like a normal distribution, then you provide a min and max value, and the software will then calculate your mean and standard deviations. And here you can pick if you want to run, the number of Monte Carlo cases that you like to run here. Okay, at the top. The same goes for these other parameters. You can pick them to be constant or uniform or triangular, etc. And then the software will just run all the cases in a bulk fashion.
Yes, maybe you can show the new feature of sensitivities where you can do drawdown, kind of compare different drawdown scenarios.
Yeah.
The same. Yeah.
That's another good one. So there's in the sensitivities, this is if you want to run sensitivities and reservoir properties. Let's say we were dealing with a gas condensate well and we wanted to look at, how does drawdown impact my EUR? So in this case, I can go in and add, let's say I want to add 3 different cases. I want one to reach my minimum BHP after 100 days, one after 1,000. And then one after 450. Then I can look at these different ways of drawing down my well, and if I get the same EUR, no matter which of these scenarios I'm doing, we know that there's no potential loss in well productivity by drawing the well down more or less aggressive. If there's a big difference, which it is for some constant wells, then we need to be careful, and we need to maybe at least consider if we want to be more conservative in how we do our choke management. So I'll just Yeah, so this is an example here. So I've defined 3 different cases, and I can save those and then just run those in a bulk manner as well. So here I'll just go and then I can compare these 3 after 1,000 days. After 1,000 days, we haven't reached boundary dominated flow for these 3 cases. So I'll be surprised if we see the same EURs, but we can take a look at the cubes. And here, as I've run it for 1,000 days, so maybe I can just go in and run them for maybe I'll do the same, just run them for a few more times. But that's basically the type of analysis you can do with that feature. Another thing that is actually new from last week is this opportunity to set a different relative permeability set in the fracture than what is just linear rel perms. So linear rel perms is just 0 residuals and also 1 in terms of the exponents and the endpoint exponents, or like the endpoints and the exponents. Sorry. So that is an additional flexibility that some folks have asked for. But most commonly it is to of course change the matrix relative permeabilities. Any other comments there, Mo? Or
No, I think we're good there.
Any other questions from the group, or? Okay. So I think at least in terms of the content, okay. Amy, perfect. So Amy asks the question: thinking of fractional RTA, is it fair comparing deltas with multiple completion changes per well? So if you're not only changing one parameter, but that you're changing a lot of parameters at the same time, not only proppants per foot and barrels per foot and stage spacing, etc., given similar geologic parameters. And that is a very good point. I think, at least to me, what I would be trying to link it to is probably number of clusters and probably cluster spacing at first. But I think that's just that's probably a study or an exercise that just has to be done on different vintages of completions and whatnot. And I haven't done that study myself, to be honest. So it could be an interesting thing to look at. Yeah, and Jonah has a very good question as well. If we're working on a multi-well model option where you can simulate the impact of spacing and timing for various wells based on a numerical match, that is a great question and a feature we are getting a lot of requests for, and that we have in our implementation backlog. One thing that we're also doing in the realm of multi-well, which is really exciting, is that in the there's like a follow-up RTA that or JIP for next year, where we have a few research topics where actually including multiple wells in the same, call it tank, in the flow material balance methodology is one of the things we want to investigate. So that's kind of along the same lines there, Jonah, on the multi-well. So definitely on the radar for kind of next steps for us. Mo, any comments there? Or?
Yeah, no, just about the question that we got from Gustavo there.
Yeah.
So Gustavo, maybe you can unmute if I misunderstood your question. But if I understand right, what you're asking about is the possibility of having a vertical lift table integrated into the numerical model, or yeah, exactly. If you have that, then you would be able to forecast your numerical model using tubing pressures instead of bottom hole pressure. Is that correct, Gustavo? That's what you're talking about?
That is correct, Bon. Thank you.
Perfect. Yeah, so in that case, that's something that we have in the backlog as well. We've got for it, and it will come. It will for sure come eventually. When it comes to the second part where you mentioned Prosper, that's not necessarily going to come because you can get the VLP table from Whitson Plus because that's where you're calculating the bottom hole pressures, right? So as long as you can get that, then you should be fine with with using that, unless you have unless down the road we find that there's a need for integrating with another software, then we don't see that at the moment. Does that make sense, Gustavo?
Yeah, Mo, that sounds good to me. Thank you.
Perfect. Very good suggestion. Thanks.
Excellent. Sounds good. So unless there's, I don't know if there's any other questions on this, the recording will be sent out, and we will, in the next course, focus more on the multi-phase flow material balance, and that will come now in August, and then the end of the JIPs and end of September. So we're getting closer to the end date here. So with that, I think we'll just say that we're done with the course today. And then if there's any follow-up questions, if you want to have a dedicated session where we go through any of these things on one of the old swells, if there was something that wasn't clear and you want to follow up, just let us know. Also, if you want to run even on these files on your own domain, just together, feel free to reach out. Happy to do that at any point in time. Thanks, everyone. Cheers.